Hello, welcome to another stream. How about that? How about that? Welcome, welcome, welcome. So, today is Monday, the day of the moon, and that means today, according to the schedule, we're programming in assembly. That's right. Hello, Auski, Tsoding TOS, Aiguduk, Salawat 23, 7001, Tekla 14, PS Comp Sai, Sirius Sergio. Hello, hello, Knazer. Hello, hello, welcome, 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 Ketchison. Really glad to see you. So, yeah, today, as I mentioned, according to the schedule, Benny Doshal, hello. We're continuing to develop our virtual machine in C. Gail, hello, hello, hello. So, since we're doing virtual machine in C, you would ask, Zozin, but in the title it says assembly. This is because we're developing a virtual machine that the bytecode of which is translatable to assembly, right? So that's why we are programming in assembly technically. So the virtual machine itself is written in C, but it's bytecode. Like currently we're working on a subsystem that translates the bytecode to assembly, and we're effectively programming in assembly. So you can't sue me for that. So yeah, sorry. Hello, start over. Welcome to the stream. Yeah. So what we were doing in the previous stream, let's actually go to the source code. It's gonna be BM. Mr. Tsoding, how do you go through I don't want to do anything days? I cry a lot. That's how I do that. So get check out master. Alright, so let's actually fetch the latest changes and see what's gonna happen. So I did a little bit of cleanup before like off screen, right? So that's why we have some changes here, right? There we go. So as you can see, I actually removed some code and stuff like that. So that's actually pretty nice. So can I remove all of these branches now? I think they're kind of useless. This one is not particularly useful, and something like 86th should be removed as well. Let's actually try to clean everything up. I'm gonna be cleaning everything up. So as you can see, our build produces a lot of garbage, and one of the things I did recently, I actually introduced the build folder. So now all of our stuff is actually collected inside of a build folder, which will probably make it a little bit easier to work with. So all of the binaries are going to be located here, right? All of the binaries here. All of the executables are also located here. I mean examples, not executables. So these are bytecodes, these are symbols for our debugger and stuff like that. Also build x8664 also puts everything there. So if you take a look at something like build example, you will be able to see some of the executables there, for something like Fibonacci, Fibonacci example, and so on and so forth. As you can see, everything works. So what we were working on the previous virtual machine stream, I think we were working on an algorithm that lets us print floating point numbers. That's what we're working on. So essentially the idea is we're going to have, at least for now, I stream for Linux? No, I'm streaming from Windows, of course. This is like literally Windows. I just customized it to look like some nerdy Linux shit. So, but in fact, this is Windows 10. So, bosom, nosm, there we go. So essentially we have a tool that takes bytecode of the virtual machine and translates it to an assembly, which you can then compile. And the idea is that that assembly has to be self-contained. It shouldn't depend on any third-party dependencies, including libc. So that's why we implementing everything ourselves. So the resulting executables, so if we take a look at some of them, so build example fib.exe. It's a static executable, it's statically linked, and if you take a look at LDD, it's not a dynamic executable, and it literally does not depend on anything. It just, you know, prints things. Nothing special at all. We have another example that actually sums up 3 numbers. I think it's called 123IXZ, and I wonder if we try to strace that thing, will it only will it show that we only call write syscall and exit syscall? yeah, that's literally what happens. This is actually very interesting. So the final executable, well, I mean, there's also exec VE, but I think it's something that comes from the bash or something. Maybe it's strace. But yeah, it literally just calls write and exit 0. That's it. So that's how self-contained it is. Doesn't allocate anything, doesn't initialize anything, doesn't do anything, just write and exit. Simple as that. If we compare that with a hello world in C, what's gonna happen actually? Like how many syscalls a simple hello world in C does? I don't know why it is important for me. It's probably not important, but I'm just curious. Like you have something like this, right? What does it do? Then I'm gonna call it like this. So here is the hello world. I definitely forgot the new line, but who cares, because we're just gonna take a look at the strace. And holy shit, it allocates some memory, it opens like it, yeah, it dynamically loads libc first of all. Holy shit, it's just a simple hello world. Can you imagine that? Like it does like all sorts of shit. So yeah, and our program actually sums up 3 numbers and just exits, and it's just 2 syscalls. Isn't that amazing? I think it's goddamn amazing. So we actually were experimenting with the algorithm that prints floating point numbers, because we need that for our self-contained executables. So this is the algorithm that we're gonna bake into our executables, and you can find the source code of that algorithm here. So yeah, we were using like a white paper like this one as a reference for the algorithm, and we managed successfully to implement that. Actually, off screen I did a little bit of changes to this algorithm. I made it support negative numbers, and I also fixed the floor. Yeah, so let's take a look actually at this thing. Origin. Okay, so it's already working. I think I showed it on one of my previous streams. Yeah, I think I showed it on one of my previous streams. Yeah, fixed floor. So the thing about this algorithm, right, is that it only works for x86 64 and only for Linux, right? If we were to add more platforms, we'll have to re-implement all of this stuff for all of the new platforms. And I was thinking, we don't really have to do that. We can just implement all of that in Buzzum. Seriously, the functions that I call native in our virtual machine. So let me take a look at its natives. It's not examples, it's not SRC, it's actually examples. It's going to be native Hasm. All of these functions, what do we have there? So like print f64, i64, u64, print pointer, whatever that's supposed to mean. Maybe even dump memory. Yeah, why not? Maybe even dump memory. All of that could be just implemented in Buzzum. So, and then the next time I need to add a new platform, I don't have to re-implement these functions, because they're going to be re-implemented automatically, because they implemented in Buzzum. So the thing I wanted to do today is, in fact, take this algorithm that we implemented in x86 64 and port it to Buzzum. Yes, and port it as a Buzzum and make it compilable to x86 64. So that's the goal for today, at least, right? So port it to Buzzum and compile to x86. It's probably not going to be as efficient as hand-coded, because like Buzzum compilation process right now is not particularly efficient, but as we add more and more optimizations, I do plan to have like optimizations when we compile to x86 64. So maybe that implementation is going to get closer to whatever we hand-coded here. Does it sound interesting? Sound interesting? Hopefully it does. So this is something that I was planning for like the past 4 days, I think, while we're not coding in, or we're not developing virtual machines. So that's the plan for today. Hopefully that makes sense. I try to explain, I try to give as much context as possible before we go, because like the project becomes more and more sophisticated, so more and more context needs to be explained every stream. So yeah. It will be some head scratch. Why? The algorithm is already implemented, isn't it? It's already implemented, so the only thing I need to do is take that algorithm in x86 64 and translate it like manually to Buzzum. Like just take the algorithm in one language and translate it to another one. It's just as simple as it can go. So why is that good? I don't know, I don't think so. No, I don't think so. Anyways, so let's go. I think I even have an issue for that. Let me start Emacs, and maybe I want to make a cup of tea. I don't know, is it too early for a cup of tea? I kind of want to have a cup of tea for that a little bit of a caffeine boost, but maybe a little bit later. So where's the issue? Print star functions could be implemented in pure Boson. That's right. You're goddamn right. So yeah, including print F64 and stuff like that. Plans to make the high-level assembly language you were talking about a month or so related to your vision of Boson future? Maybe. I'm gonna just keep developing assembly like Boson as I do, and if the opportunity will arise, maybe we'll do something about that. But I'm not sure. Like, I don't have any specific plans on that for Boson yet. I just don't have enough information to make any conclusions whether it's possible or not. So I'm just keeping developing and I keep gathering information. All right. So let me see. Let me go to the examples and natives. Here's the problem. So right now in this library we have only bindings, right? But if we start adding, like for example, we will remove this thing here, right? So we're gonna just comment it out. I think the comment is actually this thing, right? We commented it out and we're gonna add it as a function. So now you will have to call it. The thing about this function is that it will offset all of the function in your program. So the program starts executing at 0, right? It starts executing at 0, and if you include this file, it basically shifts all of your addresses and also shifts where you start and stuff like that, which is kind of meh. One of the things you can do actually in Fibonacci, right? In Fibonacci. So you have the main here, and you include it, and now the execution will start from here, but not from the main. So the thing you'll have to do all the time, at the top of the file, at the top of your like input file, you'll have to jump to main by passing all of the stuff that got included here, which is not particularly a good idea in my opinion. I think we should like finally, you know, shave the yuck and introduce an entry point like this. Right, introduce an entry point. Yeah, there we go. So essentially, no matter like what you do, you can actually put this entry point somewhere here, just a preprocessor directive. So the final executable, you know, will know that you have to start from the main. So we'll have to extend the format to support the entry points, and we also have to extend the assembly, specifically preprocessor directives, to support an entry point directive. So, and also the assembly should fail if you never provided an entry point. So yeah. This is probably the first thing that we'll need to do here, right? So you see the problem? You see the problem? So once we start to actually have libraries that implement something, I think we should start, you know, thinking about this kind of stuff. It reminds me of org assembly instruction that you have to put on the first line of com file in Windows, talking about, yeah. Yeah, it's kind of like that actually. If you think about it, it's just like an offset, or right, that explains where you have to put things, and yeah. It's basically it's actually as close as to COM as possible. It's probably even more sophisticated than COM, but yeah. Imagine using ELF in 2020. Anyway, so let's go ahead and do that. So I'm gonna create a separate branch. For all of that stuff is gonna be like this, and what we're gonna start with, I'm thinking we're gonna start with extending the format. We're gonna start with that. I think we're gonna start with extending the format, and the assembly will put the entry to 0 by default. Right, and once we have the format supporting the entry point, then we can extend assembly to actually demand the entry point directive. I think that's how we're gonna go about that. That's how we're gonna go about that. All right, so let's go to BM and let's find the BM thingy, the BM definition of the machine. So this is a Boson, this is not BM, but where is BM? Here is BM. Would you look at that? Would you look at that? So, oof. Oof. So we have stack, program, natives, memory. I guess I can just introduce something like inst address entry. Right, there we go, inst address entry. And also, since we're extending the format, oh maybe, yeah, only the format needs to be supported here, right? So you have magic, version, program size, memory capacity. And the question is, where are we going to put the entry? It feels like maybe it has to be put after the program size because it's related to the program. That will be like kind of correct thing to do, but maybe it will be better to put it like at the end somewhere here. Since we have a versioning, so I don't think it's that big of a problem, right? It's not that big of a problem, so it's a different version of the format or whatnot. We have not established the format anyway, so it doesn't really matter. Okay, so we're gonna have an entry. Hello, this is Dead Alive. Please speak English. This is an English-speaking stream. Thank you very much. All right. So entry. And where is the BM file version? Is going to be the 5th one. Breaking changes. We make breaking changes pretty much every stream. What are you talking about? All right. So BM file meta, right? BM file meta, and so this is where we load the program, right? This is where we load the program. Then we check all of this stuff. Everything looks okay. Everything looks okay. So another place where we're gonna be doing this thing here, BM file magic, BM version. Okay, so this is what we're saving here, right? BM file version. Since I'm not setting it here anywhere, I think it will be automatically filled with 0. So that means, yeah, automatically the file format already supports an entry just by me adding an entry into the executable. So that's nice. All right. So another thing we'll have to do, we'll have to go probably through the debugger and make the debugger use the entry point to start the execution. So that's going to be very important in my opinion. All right. So let's actually try to build all of that and see how it goes. Does it fail? It doesn't seem to be failing. Yeah, everything seems to be okay. We do not approve of racial slur on this channel. All right, so yeah, this one, oh yeah, it actually removed the thing here. Alrighty. 105, introduce. This doesn't look like assembly. Because you missed the beginning of the stream, right? So we're actually implementing all sorts of things in all sorts of languages. Hello, Witness, welcome to the stream. Introduce entry point to the BM files. So we're developing a virtual machine that has its own assembly. So right now I'm extending the format of the virtual machine so it can facilitate the features that we need to implement some particular algorithm, and then we're gonna start programming an assembly. Does it make sense? Hopefully that makes sense. All right. So the next thing, I think I need to now go to BME, and BME just loads this thing. Okay, so load program from file, right? It's kind of funny, like when you load a program from file, right, you can just go ahead and set IP to the entry, right? So, and call it a day, right? You can just call it a day. That's right. So here's the program size. You load some sort of a memory. Where's the program? Okay, so in some way here you can just literally do something like BM. Is it called BM in our case? Yes, it's called BM. Entry, actually not entry, but IP, meta entry, and that's it. You can call it a day. Dipyra subscribed with Twitch Prime, your first subscription, by the way, thank you so much for your first subscription, and welcome to our epic virtual machine club. How about that? How about that? Isn't that amazing? I think it's goddamn amazing. So yeah. Thank you so much for the support. So we can do it something like that, and that way we don't even have to like extend the format of this virtual machine, right? So we don't have to add an entry. But the thing is, things like debuggers, they will probably need to restart the machine, right? So that's why you need to keep track of the entry. On the other hand, the debuggers can, before executing, so after the debugger loaded the VM, right, they can save an entry point to somewhere, but at the same time the structure makes it not really obvious that you have to do that. So that's the problem here. Like, it's not obvious that you have to save IP and to restart it and stuff like that, and that IP is an entry point. It's just like, it's kind of confusing. Maybe we should add entry here just in case, for like, I don't know, feels like, I don't know, it's kind of a bike shading situation, so I'm not gonna do it right now. We'll see. So yeah, essentially the virtual machine just gonna add, so loading process is gonna just set the entry point like IP there, and then you will have to do that yourself. So, and the cool thing here is that we don't have to modify BME. The debugger should reset the whole BM state. Yeah, true. Well, it doesn't really have to reset everything, it only needs to reset memory and stack. The program is not modifiable, so the program, yeah, can stay the same. So yeah, probably makes sense. So in the easiest way in that case would be probably reload the whole file. Yeah, so I think. In any case, in bdb.c, it's gonna be halt. Okay, and then we don't even touch IP that very often. Right, and that should be okay actually. That should be literally it. That should be literally it. Do I wanna test something? Yeah, let's do some tests. Build SH, there we go. And then I wanna run one of the programs that we built, right? I wanna run one of the programs that we built. So it's gonna be build example fib bm, and let's see. Yeah, it still works. Nice. And I want to test if it's gonna break if you try to add something to the standard library, right? So we're gonna go to the standard library, natives, and I'm gonna add hello, which is not gonna do anything. Might as well actually just push like a bunch of numbers, like 1, 2, and then just sum them up, and maybe drop the result, whatever, just some instructions, right? Yeah, look, chat, look, I'm programming in assembly. That's what you were waiting for. I'm programming in assembly. Isn't that amazing? I think it's goddamn amazing. Is the VM just for fun? Well, my entire life is just for fun, so I don't know. Yes, I guess. Hello, Yatanasa, welcome to the stream. Okay, so hello is already bound, really? Okay, so let's actually do something like this one then. Okay, cool. And if you try to run this entire thing, I think it should break. Yeah, there we go, it broke. It literally broke. It's for job. Yeah, it depends on the definition of a job. So let's discuss what do we call a job. All right, as you can see, like you cannot just add this thing here. Just some garbage. There we go. So to combat that, we need to introduce entry point to the assembly. How are we gonna do that? So before we're gonna do that, I want to commit this thing. It's gonna be 5 make bm load program Program from files, support entry points. There we go. Cool. So now I'm gonna go to the bosom, to the bosom context, right? Where is the bosom context? Here is the bosom context. And we have program operands, blah, blah, blah. And I'm going to introduce instruction address entry. But we wanna require the user, the programmer, always provide the entry point. We want them to always provide that. So, and we also need to follow the zero rule, meaning that the zero initialized structure here is a valid structure, and in that valid structure, the entry point is not provided. Right, so that means entry point is going to be initialized with 0, but 0 is a valid entry point. So to indicate that entry point is not provided and follow the 0 rule, we'll have to introduce the boolean. What's up, old man? Welcome, 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 welcome. How are you doing? So yeah, let's say something like has entry. Right, has entry. So I could have probably done something like maybe like this, but unfortunately I'm not programming in C++, that's why I have to add this boolean here. Zero rule, we learned about yesterday. Well, this is like the rule that I follow for the past like several years already, I don't know. Okay, cool. So now I'm gonna go to bosom translate source, and that one is gonna be very interesting. So here is the whole translation process, right? We have a whole translation process, then we have a second pass. Could you use some unaligned address as an initialized entry point? Unaligned address. What is the unaligned address in terms of virtual machine? As an initialized entry point. What are these concepts? We don't have any of these concepts in a virtual machine. I think you make too many assumptions about this project as usual. So yeah. Let's make a cup of tea, I suppose. So I want to make a black tea. I'm really running out of tea, by the way. Here, it again. Okay, so did I run out of? Yeah, okay, I think I ran out of black tea completely. So that means the only tea that I have left is Oolong Max. Yes, apparently, like, yeah, I had like oolong for quite some time, but I didn't know that because I was drinking just black tea. And when I ran out of black tea, I just realized that I also have oolong. So that's what I'm drinking today. Not particularly a big fan of it, but it's okay as a replacement for Earl Grey and black tea. I think it's good. Does anyone have any questions while I'm making a cup of tea? Does anyone have any questions to the God Russian hacker? Tried for? Yes, I tried. That's my whole reaction to it. Hello, Poly Insecure. Welcome to the stream. How are you doing? We're making a Oolong Max tea. It's a C reference. Alright, so I'm gonna go quickly to the kitchen, turn on the kettle, don't go anywhere, or yeah, I'm gonna hack your mom then. That's right. I'm a Russian hacker. I can hack your mom. Hello. So the thing here is very interesting. It's our insanity, yeah, probably. So the translation is actually recursive. So where do we check for entry or not? We have to check for a provided entry in the bosom itself. So let me go to the bosom executable. So this is where we do all of the translation, right? So yeah, and if bosom has entry, right? Oh my god, entry doesn't have an entry. We have to throw an error. Use of PGA DM hardware similar to turn your kettle from Emacs to do T when. I don't know. Okay, error. So it's gonna be F std error. Entry point for a BM program is not provided. Use preprocessor directive entry to provide the entry point. You can use Darjeeling tea. No, I don't even know what that means. I'm sorry, man. Never tried it. Entry performance is not providing. Use preprocessor directive entry to provide the entry point. So usage, and I want to probably show a couple of examples. So it's going to be fprintf std error. It's going to be entry main or std error entry 42 and so on and so forth, right? So these are just examples, and I think I can just show examples, right, like this. Already better errors than GCC Plus LD? Yeah, probably. I mean, it would make sense to actually document that properly. Default 0 is a good thing to allow. I don't think so, because includes constantly shift them, right? Includes constantly shift them. So it's better to train people to provide the entry point, in my opinion. People, who are those people? I'm the only one who's gonna program this shit. So anyway. So yeah, if you don't have this entry point, it's gonna fail instantly. Okay, so oh yeah, this is what we'll have to do. What's up, Corporate? What's up? Welcome. And there's also A in here, and the full rebuild should fail. There we go. Entry point for a BM program is not provided. Use preprocessor directive entry to provide the entry point. Examples, there we go. So, and it fails in specifically memory example. Let's actually go to be fair, we also need to indicate the file where that thing fails. Copy-pasted, hello, yeah, I think I already said hello to you, welcome. So we do have a file path, right, input file path, so I think I'm gonna actually provide it here. It's gonna be like this. Input file path, so let's try to recompile it one more time. All right, so yeah, so this is where it actually fails. Memory bosom. So, and here's the thing, if you try to use this thing right now, right, main, it's not gonna work because we don't have such a directive yet. You can actually put it anywhere. Once it's implemented, you can put it anywhere. There we go. So, unknown preprocessor directive entry. Imagine being told by the compiler, use this directive, and then use that directive, and compiler tells you, unknown preprocessor directive entry. Yes, it's fucking classic. Fucking classic. So the next thing we need to do is to implement this directive, of course. So that's the next thing, of course. So here's the bind, here's one preprocessor directive, here's another one. And after that is going to be else if like that. So I forgot how to parse arguments of the preprocessor directives. So this one has to be an entry, right? And at the beginning of the preprocessor directive, what we usually do, we usually trim the line, maybe, I guess. Yeah, I guess we just trim the line. Right, that makes sense. Sounds like Rust C, a known function X, did you mean Y and then the known function Y? Yes. On top of that, do we have to handle the... yeah, we don't have to do that, so it automatically removes that stuff from us, so that means we can use line as the name of the parameter. Nice. Nice. That's pretty cool. That's pretty cool. So this is label binding. So we need to take a line and treat it as a label. And treat it as a label. So I think my kettle is ready, so I'm gonna quickly go to the kitchen and just pour myself some hot water, and then I'm gonna go back. For nested ifs. Well, some of the stuff could be actually moved to separate functions, but the problem is that that function is going to be literally used in a single place. So, I don't know. Sometimes you want to write big functions. Sometimes that's what you do. Sometimes it's okay. Hello, welcome back. Do we have a function that accepts a string? And if it's a string if it's a literal, it tries to handle it, and if it's not a literal, it tries to resolve the binding. I'm not sure if we have such function. So it depends on how exactly we handle the literals in an actual assembly. So here's the parent count. Oh, translate literal. We literally have a function. Translate the literal. Okay, so that's cool. I didn't know that. Translate the literal. It tries to, yeah, it tries to parse the string as a literal, and if it's not a literal, it will return you false. And if it's not a literal, you can try to resolve the binding. You can try to treat it as a binding. So this is actually quite cool. So this is exactly what we're gonna do. So it's gonna be entry. Maybe I'm gonna go back and just copy paste it here. So entry, come on. So this is the first step we want to do. If this thing fails, we need to do something like bosom resolve binding, right? So this is the second step. Resolve binding, cool. Okay, if, well, first let's translate the bosom itself. Then we provide the input. The input has to be a line, and the output is going to be the word. The output is going to be the entry, I suppose. Well, it is a word though, right? And our entry is not a word. It's a address. It's an instruction address. Okay, inst address. It's an instruction address, and we're going to call it entry here, so it's going to be 0. Well, I mean, I have to make it a word. And I'm going to 0 initialize it. I think this is how I'll have to do that. And an entry. Cool. So if not a literal, right? If it's not a literal, we have to try to resolve the binding then, right? We need to try to resolve the binding. Okay, so we provide the bosom, then the name is going to be the line yet again, and the output is going to be an entry yet again. There we go. And if that didn't work, right, we have to throw an error. What's interesting is that we can actually put that into short-circuited OR. Who watched John Blow today, by the way? Did anyone watch John Blow, like, right before the stream today, like during the morning, where he was just doing short-circuited OR, and he was asking, who even used short-circuited OR? Like, why would you use that? Nobody uses it ever, so let's not implement that. Right, and here's me literally using it. Yeah, you saw that. Yeah, now here it is. Here's an example. So I try to translate it as a literal, and if it fails, I try to translate it as a binding. And if that fails as well, I'm gonna throw an error. So yeah, that's why I want to use it, because I don't want to resolve the binding if I translate it to. Okay, so why are you not trusted, by the way? Jizbian. There we go, you're trusted now. Right, because you watch John Blow, so you're automatically trusted. Alright. So that's a good example. Yeah, short-circuited evaluation, yes. It's a pretty old concept. It's been in languages for quite some time already, so yeah. So I'm just pouring a cup of tea. Don't mind me. What did you think of the game? Nothing. I'm not really a game developer. Enjoy? What? Are you talking? Oh, you're talking about tea. I see. What kind of tea? Oolong. Hello, really WTF? Please speak English. This is an English-speaking stream. Nobody understands you. You watch John Blow, trust you. All right. Cool. So what we're gonna do here, if all these things fail, so this entire thing will fail only if the binding is not correct, right? If you don't have a correct literal, well, you're gonna try to do it as a binding. Oh fuck, yes, I forgot that it's a... Okay, yeah, this is a fucking title, that's why we have all these people speaking Russian. So what should we replace it with? What should we replace it with? Code in an assembly. It doesn't even work that well, so we definitely want to change it to something. Well, let's remove Russian, I suppose. Alright. Assembly hacker coding. Okay, so that's actually pretty cool. Assembly hacker coding. Yeah. So that was really dumb of me to actually put word Russian in the title. So okay. Eastern European hacker, yes. American with a Russian accent. So, sounds like Probot. Alright, so what we're gonna do here, std error, and yeah. Oh, by the way, I wish Zhiyang was here, but I recently started to adopt this interesting paradigm for printfing custom types. So we have a custom type string view, right? Have a custom type string view. And the problem with printfing this type is that it's a sized string, so, and it's not null terminated. So you have to use this thing to printf it. So what I did essentially, I created a separate macro as svfmt for a format string, and a macro that unpacks the string view into a sequence of arguments for printf. And now if you have a string view, you can actually print it like that. So on the place where you want to print the string, you put svfmt. Since string literals can be sort of concatenated at compile time like that, you can do that. And then as an argument you provide svarg. So this is a pretty cool paradigm, and I'm starting to use it throughout my BM code base. And it works basically for any simple custom struct types. Quick question: what would you expect a junior programmer, new grad, to be able to do? Thanks. That's a really strange question. See, yet one of those questions is, what is the definition of the junior? Like, I'm not interested in discussions of the definitions of words. I think they're the most boring discussions that you can ever have on planet Earth. I'm really sorry. Like, what's the definition of a senior programmer? What's the definition of junior programmer? Who fucking cares? It's boring. Let's just do something. I'm sorry. Like, it's just like, people ask me this kind of shit all the time. It's just like, it's not interesting. It's just, it's like, you know, like when the answer can be boiled down to depends on the definition, I lose interest in the conversation instantly, because yeah, it depends on the definition. What else do you want to discuss? No, it's whatever. Who cares? Let's make something interesting. Okay. So I introduced this thing. So this is interesting, by the way. This kind of like format strings like paradigm is interesting. What is junior is not fucking interesting. This is interesting, okay? So because this is such a like cool paradigm where you can have like printfing custom types, right? And I wonder why not that many libraries in C actually adapted. I didn't really see that paradigm being used that often. Right, so yeah, and it's kind of strange, like especially the macros that unpack the arguments. It just makes everything so fucking easier. The idea of printf generally sucks, but I think this makes it suck less. So it allows us to work with what you have, like it allows us to do what we can with what we have. So yeah. Wait a second, what is that? Oh, it's a permaban. Okay. There we go. So, let's continue. We have so many permabans today. This is really strange. Is it something with me today? I don't really know. I'm not really tilted today even. Maybe it's title? Maybe it's title, I don't know. But tilted. I don't know. So it's just like, I mean, you could have like, I don't know, expressed the same idea without violating TOS at least. I don't know. It's not like I care about people insulting me, right? I more care about people violating TOS. And yeah. Anyway, what is the next thing? Yeah, so this is an entry thingy. An entry. We're doing an entry. And what I need to print here, I need to print where exactly that happened, right? So essentially, if you fail to provide a proper binding, right, we want to give you the place where that shit happened. I think it does make sense. So it's going to be svfmt, right? svfmt, like this, error. So I think we have like unknown binding. Yeah, we already have that unknown binding. Where is the entry? Where is the entry? unknown binding, and we can use this format string yet again. We can use that format string yet again. That's cool. That's cool. Unknown binding fmt sv arg, and this one is going to be what? It's going to be file name. Where is the file name? It's an input file path. It's an input file path. Then we have a line number, and then we're gonna have arg, right? So this is gonna be arg, and what we're gonna put here, we're gonna put the line, right? So this is essentially gonna be the error, right? This is essentially gonna be the error. And in memory, I'm using entry main, but what if I never had this entry main? So let's actually see what's gonna happen if I try to compile that. Is it gonna fail appropriately? Unknown binding main. And we go here, here it is. So to add this binding main, we'll have to put it right here. All right, if I try to rebuild that, it should fail in a different place. Unknown binding main. Oh, really? It still thinks that it's unknown. Oh, shit. Aha, I see. Because it's not fully resolved yet, isn't it? I think it's not fully resolved yet. I don't remember how many months ago Zozin unboxed new battery, but old one is still not replying. Stop shaming me. Like, it's really difficult for me to motivate myself to do things. Okay. So people think that I'm somehow easily motivated to do shit, but I literally cannot replace my battery. That's how bad it is. So you guys think I'm joking, right? That I cannot motivate myself? Here is the proof. Seriously. You need donation goal to replace. Donation goal is not gonna help. Trust me. Donation goal doesn't help. So money do not. I already said that money do not motivate me as long as I have a place to live and something to eat for the month. If I have enough to just eat and live and sleep somewhere, money stopped motivating me, like, completely. There's like zero motivation. So yeah, I don't know why. It's just like, this is how my brain works. They only motivate me when I'm actually gonna be starving the next month. Seriously, only then. Oh, okay, I need to start finding like a source of income. Okay, so that means I'm gonna start doing things. Yeah, it's actually hard, believe it or not. Donation goal is not gonna help. All right. Froggle, it's not even 5 head. It's just like something with my brain. Like, it's just, I don't know. Maybe this is because I was born in a poor family and I like just grew up frugal in general. And I cannot get rid of that mindset. It's just like difficult for me. Even though it's not like a problem for me now. Like, I'm not really poor now. But still, anyways, here's the thing. We need to treat this stuff similarly how we treat the entries. So essentially, if you encounter a label, right? If you encounter a label, you defer its resolution, but you have to do that not for the instruction, but rather for the entry point. That's what you have to do. So that's how it's going to work. All right, so maybe we can. That means we'll have to add more stuff into the bosom context. So we have entry, has entry, but here's the thing. Like, entry could be also a literal. We should allow the literals there as well. So let's put it this way. It's going to be string view. Deferred entry binding name. Yeah, so I don't know how to call it, but that's what it is. It's a deferred entry binding name. And yeah, so essentially if you try to have an entry as a binding name, it has to be deferred and resolved on the second pass. So we have a two-pass assembly, by the way. We have a two-pass assembly. Yeah, okay, let's try to do that then. It's gonna be entry. All right, so here's an entry. You try to translate the literal. Then here is the thing. Here is the thing. Then you try to. You're not trying to resolve the binding though. Right, you're not trying to resolve the binding. So here is a translate literal. Two pass. Well, I mean, yeah, we have a two-pass compiler. It is what it is. So what we're doing here instead is essentially entry bosom entry deferred entry binding name, and it's equal to line. That's it. That's what we're doing here actually. Otherwise entry is going to be equal to like bosom entry actually. Bosom entry is equal to entry as U64. That's how it goes. So I'm translating a literal. If it's not a literal, we're going to treat it as a deferred entry binding name. There we go. And on the second pass, right, where we, you know, doing all of this stuff, only then we're trying to defer this entire stuff. Second pass liberation doesn't report the location in the source code. Yeah, this is actually pretty big problem. So we may try to solve that again. All right. Okay. What's up, Ken Jain? Welcome to the stream. Welcome, welcome, welcome. So we need to do resolve thingy, right? We need to do resolve thingy, but we need to do that only if you don't have an entry. All right. So let me go back. It's gonna be entry. And after all of that, I think we need to do bosom has entry, right? True. There we go. Another interesting thing, if bosom has entry, we need to complain. I think. What do you guys think? Because you already said an entry. It would be also nice to tell where exactly the entry has been set. In terms of location, but I think it could be a separate issue. But maybe we can try to do it right now. All right, so it's going to print f std error, and it's going to be svfmt d, and what's going to be error. Entry point has been already set, right? So this is going to be something like this. So we have to specify the location is going to be svarg. The location is input file path and also line number. And then we're going to just do exit with what? Excuse me. To do entry point already set error does not tell where exactly the entry has been already set. I think it's quite important to have that information at some point, but yeah. So after that it has to be true. Okay, so it is true. This is really strange. It's a little bit complicated, but it's okay. Second pass. And we need to check that the entry point is deferred, right? We need to check that the entry point is deferred. How can we check that? If bosom entry, or maybe it's called deferred entry binding name is greater than 0, then it is set. But it could be that the line is actually empty. Okay, so we need to guarantee that this thing will never be empty. We need to guarantee that somehow. How can we guarantee that? We can try to guarantee that by checking that the line is not empty. Right, checking the line not empty. Okay, we check that we haven't already set the entry, and then we can check the size of the line. If line count is equal to 0, that means, well, that's an error. fprintf std error. So we can say something like error. Literal or binding name is expected. Right, so we're gonna actually put it like that, and it's gonna be simply sv-arg input file path line number, and then we're gonna just exit with 1. Okay, so that means that whenever we get a deferred entry binding name, it's gonna be greater than 0, and that indicates that we have something. Okay, so and another interesting thing, I think we only should try to do that if bosom has entry, right? So the entry has been provided and we have deferred entry binding name, right? So only then we try to defer it. Okay, makes sense. So what we have to do here is just word output, right? It's also word output, and let's try to do that. Cool. So binding is bosom, name is deferred binding name, right? It's a deferred binding name. I'm going to put it here, and we try to save that into the output. Here's the output that we're trying to save. If that thing failed, right? If that thing failed, we should throw an error, right? So we should throw exactly this kind of error. So, and since this issue is not resolved, we cannot say exactly yeah, we cannot say exactly where that happened. Okay, so that looks cool. So it has entry and it's also deferred, and yeah, cool. Now, so here's the output. We can do that. What else do we have here? So arg name. Yeah, so we have to do it like this. So it has to be this kind of name. Cool. Cool. Nice. It compiled. Memory compiled. Look at that. Memory compiled. Beautiful. So we can even try to do other things in memory, right? So I suppose just put something that never existed before, right? And it's a known binding this thing, and then I can say main, and it does compile. Okay, we managed to do that. We managed to shave a yak a little bit. So now it complains about fib example, right? In the fib example, we don't provide any entry point yet, so let's actually quickly do that. So it should be as simple as just providing entry main, right? So this is the entry here, and we have to do that for each individual example here now. So we have to do that for each individual example. So yeah, we managed to do that. So in this particular case, well, it's always nice to have like main, in my opinion. It's always nice to have main, and then just do entry main. So maybe it would be nice to sort of mark For the OT question, off topic, okay, but I'm curious if any Russian hardware CPU are developed but who cannot speak Russian cannot access to their resource. I read that for URSS CPU was able to compete with Intel. I don't really follow that. The only thing I know about Russian CPUs is Elbrus, but can it compete with Intel? I don't think it can compete with Intel. And I don't think it's a good example of not being able to access if you don't speak English. You speak Russian. I don't know. I don't really know that much about that. I'm sorry. All right. All right. So what do we have? So here's another one. It's 1, 2, 3, 4, and this one is also going to be main. So now, no matter what we're gonna put in the standard library, it's not gonna affect anything, hopefully. But it's just, I just have to go through each individual file manually and just add the entry here, which isn't okay, I guess. It would be also nice to check all of them. So where is the? We don't have to do jump main here anymore. It's not needed. We can just do entry. So now e-calculation. Do we even have main here? No, we don't. All right. So this is main. Then. Rod 13. Yeah, I remember this one. GMP main. I seem to remember hearing about some Russian CPUs being ternary, I mean. Yeah, there was one of those, but I mean, it was just experimental and it never really took off that much. So, and it was a really old, like a long time ago. Technology that was used for ternary operator at that time to this day is completely obsolete. So technology was actually similar to magnetic cores. So even if we try to adapt that, so whatever USSR scientists used, it's already so dated to these days. It's like pointless to even consider that. It's just like something similar to magnetic cores. It's not like exactly magnetic cores. It's just like something like close to that. And the way they achieved the treats is basically they developed a cell that consists of 2 binary cells. So the combined cell actually has 4 states, but the fourth state was thrown away to achieve the ternariness or whatever. It was really strange like approach. I don't know. I actually looked into that a little bit, but it's okay. It was interesting at the time, maybe, but these days it's maybe for historical reasons. I don't know. Discovered your YouTube channel. Is there any plans for more videos? I guess, I don't know. We'll see. There's not that many interesting topics I can come up with to put on that channel. We'll see. The problem is that making videos on YouTube, the videos that I put on that channel is actually very time consuming, so it's just way easier for me to just stream, right? So yeah, I don't really have that much motivation, but maybe some interesting topic will pop up that will make me want to make a video about that. We'll see. It's like you know, the topic on dynamic programming in Haskell. I think it was interesting enough for me to, you know, finally made a video about it. Because I think it's kind of cool topic, and not that many people are talking about it, especially people who teach Haskell, because it's kind of an advanced exploitation of the laziness of the language, and I think it's really interesting. I don't really fully understand it myself, but yeah, it's interesting nonetheless. Alright, so here's another thing. Okay, so main, entry, main. So there's also hello. So let's put main here. So hello, if I remember correctly. Oh yeah, it's just Prince Hello World. Alright. I've met Simon Peyton Jones, really nice guy. Cool. I'm really glad. I'm not that big of a Haskell fan to actually want to meet one of the Haskell creators, but I mean, I'm glad that you enjoyed, conversation with him, I suppose. Yeah. People think that I'm some sort of a Haskell fan, but I really don't care much about Haskell. It's like it's a pretty cool for intellectual masturbation. So yeah. Okay, Jesbian, you're welcome, I suppose. What is going on today? It's a really strange day. Like, streaming is really weird. Like, so at the moment, like, for a moment, there are people who tell you to kill yourself, and then after 5 minutes, people are thanking you for making a good content. Being a streamer is weird, not gonna lie. Being a streamer is weird. But yeah, I guess you kind of get used to that after some time. It's just like, yeah, you probably need more tea. Yeah, this is exactly my face every time I'm masturbating, Haskell. You are a pioneer. In what? Pioneer in what? I'm not really sure what I'm pioneering here. I'm not sure if I'm doing something particularly new. But yeah, okay. Streaming. I'm a pioneer in streaming, trust me. There were streamers before me, so it's like, it's already well established. It's already well established area. I'm not pioneering anything at all. So okay, cool. So this is another thing. And if you want to say that I'm pioneering programming streams, I'm not pioneering them either. It's also a really well established area too. So you probably didn't just didn't watch enough streams in general, and maybe programming streams. Pioneer in virtual machine research. I mean, WebAssembly as it is right now is way cooler than virtual machine, trust me. Right, so if you take the specification of WebAssembly and read it, it's way cooler than virtual machine. But maybe eventually virtual machine is gonna get closer to the WebAssembly. One thing about WebAssembly that is cool is that it's statically typed, and before executing, you actually have to verify the types, and there is like a established algorithm of verification that you're not going to try to sum up numbers that are not summable together, right? So you're not like trying to sum up like integers and floats without converting float to integer or integer to float or something like that. They actually check that. That is so cool. And they do that on a stack machine, and you verify them by doing some sort of like meta evaluation of the virtual machine, where instead of values you use the types of the values, and it's actually, the algorithm is explained in the specification of WebAssembly, and you have to do that before actually executing the virtual machine of WebAssembly. This is so fucking cool. So yeah, I'm not pioneering anything. WebAssembly is way cooler than virtual machine, trust me. But I have some other interesting ideas. So, all right. Also, they have an interesting concept of blocks that you can branch out from. So essentially, the blocks make sure that you're never gonna jump into an invalid instruction, or in between an instruction or something like that. It's actually super cool. I mean, it's 10 years of streaming more or less, but this way of interacting between people still embryo. No, it's not actually. Trust me, like, people been doing what I'm doing like for for decades. It's just nothing new particularly. You just probably didn't watch enough streams. Alright, so I think I actually introduced the entry point, right? So we have a notion of an entry point, and what I want to do here is, you know, test all of the examples. So can we try to test all of the examples? Let's go and test them. So here are all of the examples. So there's a lot of them, and I should just go ahead and run, like, test the examples on the CI. That would be actually kind of cool. Right, basically run them in some sort of environment where you try to observe the output of the example and compare it with the expected output. What's interesting is that in the future, right, we're not going to have print, like too many printer functions, right? So we're only going to have one single native print function, which is write, which accepts the pointer to the memory, the size of the buffer, and just prints it. So all of these functions, print I64, print F69, are going to be implemented in terms of that write native function. And the way we're going to test examples, we're going to basically set up environment where the write native function basically outputs to some sort of a memory. Right, it basically doesn't print to the screen, but it outputs to the memory. And then after executing an example, we're going to look at the memory and compare it with the expected output. So we're going to basically execute this example in a sandbox memory, and this is the way we're going to test that the programs actually work correctly and output the correct stuff. And yeah, it will not matter if they're using some sort of like a weird printer, because all of these printers are implemented in terms of the write native function, and write native function is provided by the sandbox environment. So, and the sandbox environment basically can observe what the programs are printing. I think that's the way we're gonna run the examples on CI and verify them and test them every time we make any sort of changes. So that's my idea. Does it sound interesting? Maybe this is something we can work on. Isso. Kawaii desu. Anyways, so what I need to do, I just need to go through all of these examples. So the first example is going to 1, 2, 3, F, right? 1, 2, 3, F, PM, and let's just execute this motherfucker. It's actually 3. English is hard. BME, I'm not talking. Oh, would you look at that? This shit is broken as fuck. It's already broken. It's nice that they try to execute it first. It's really nice that they try to execute it first. Okay, first try, by the way, failed with first try. So here it is. Native print F64. Is this because I fucked up something in the native? No, I didn't really fuck up anything per se. It's just really strange. Okay. Let's maybe go to the BDB. Maybe we can execute it with BDB. If I remember correctly, BDB doesn't try to mess with IP, right? So if I take a look at the IP, yeah, in the main, let's go to the main function. And in here, yeah, it doesn't set IP to anything. It's just, you know, print the IP. Oh, that's actually pretty cool. So I can do something like this, and I can say print the IP, and IP is 0. Which is not particularly correct, is it? Which is not particularly correct. Okay, so maybe there's something fucked up with the entry or whatnot. So, and then you can start the execution. So we can break on main, right? So breakpoint is set at 5. Oh, okay. But the IP is 0. But IP is 0. Huh. So main is okay. So if I try to run this entire thing, it basically started at 0. Holy shit, what the fuck was that? Wait a fucking second. Alright, that's very interesting. I know what is going on. I pressed Control D. Okay, so let's actually report an issue for that. It's like you press Control D and BDB freaks out. What the fuck do you fucking mean? Look at that. It's just so beautiful. This. Wait a second. I love it. I kind of vaguely understand what is going on there, but I'm gonna report the issue first because I don't really want to shake that much of a yak. So BDB freaks out on Control D. There we go. So that should be enough of an explanation. So yeah, maybe I'm gonna take a look at that, or maybe you heard some plots may want to take a look at that. Oh yeah, here it is. Here it is. So basically, the loop doesn't check that the standard input has been closed, because by doing Control D, you essentially close the standard input, and that's why this thing continued executing. I don't understand the yak meme, so I just pretend to laugh with everyone. Yak shaving, it's an English idiom. Yak shaving. So the idea is the following, right? So for example, what I wanted to do, initially I wanted to port my floating point printing algorithms to bottom. I cannot do that because we don't have an entry instruction, and without entry instruction, adding anything to the standard library is going to fuck up the entry points of the example, so I need to introduce the concept of entry function. While doing that, I was using the debugger, and debugger actually is bugged, right? So I started to work on this problem of fixing this problem. But my initial goal was just port functions from one language to another. How did I end up here? This process of constantly just branching out to different problems is called shaving the yak. So do you understand what this? We can actually read the actual definition, yak shaving. So maybe there is a better explanation. So maybe Urban Dictionary actually explains it a little bit better. Any seemingly pointless activity which is actually necessary to solve a problem, which solves a problem, which several levels of recursion later solves the real problem you're working on. You see, that's what it is. So that's the yak shaving. So it's actually a pretty convenient concept, because that happens every fucking time. So yeah. So playing Factorio, yeah, is essentially, I guess. So it's basically sodding stream, yak shaving. All right. Playing any adventure game, probably. Cool. So I think the loading of the program is fucky-wacky. That light bulb seen from the Malcolm in the middle. What? I don't know what you're talking about, dude. Alright, so we have a meta. Alright, we have a meta. And meta entry is set to IP. So that should be working. Unless entry itself is not set correctly. It may be not set correctly if bosom save to file also does a fucky-wacky. Does it do the fucky-wacky? Yes, it does. We never actually set the entry. So the entry is set in bosom, but we never actually save the entry into the meta. So it has to be something like this: bosom entry, and yeah, something like this. There we go. So that's why it never actually worked. So we caught that problem. Let's try to recompile everything. This one. Oh yeah, I remember this one. Yeah, this is actually perfect example of yak shaving. It's literally that. Yes. Okay, so I think I know what you're talking about. Wait, by the way, why the fuck are you not trusted? Let me actually trust you. Serious Sergio. because you've been around for quite some time. So yeah, I think the time has come to fucking trust you. Okay. Cool. So can I now take a look at this example? And now we can try to print IP. And IP is still fucking 0 for some reason. And if I try to run this thing, it still underflows my stack. So this is really strange. Did I forget to rebuild everything? I didn't think I did. It still fucking fucks. Still doesn't do shit. Okay, so if I try to do BMI, it does. Why? Just why? Nice one. It's really strange. If you don't have an entry, you will complain. Let me go back to BM and translate bosom, translate source. So where is the second pass? Where is the second pass? So, okay, we extracted the binding, but we never actually set the binding to anything. So let me quickly do that. Bosom entry set to output as U64, and that should do the trick. That should do the trick. Okay, so if I try to run it now it is run perfectly. So I can even take a look at BDB, and if I take a look at the IP, so you see, it tells us that IP is 5. Beautiful. Oh my god, I really hate it, because I have a reflex to quit a lot of programs by pressing Ctrl D. Like, I actually turned it into a reflex. I think we need to shave that yak, because it fucking annoys me. Yeah, time to shave a yak. Alright, because it really fucking annoys me. So let me go and maybe commit whatever we have already. So 105, introduce entry point, the concept of entry point. I'm going to push that right into the repo. Right into the repo. Cool. And so let's switch back to a different place. Right. Let's switch back to a different place. And let's create a separate branch. Okay. So in here, I'll have to rebuild everything from scratch yet again. So we always rebuild everything from scratch. And then I can try to do BDB, right? And then I can press Ctrl D and it fails miserably. So how can we actually fix that? Is there any easy way to do that? So when I press Q, it just exits successfully. That's totally fine. So we're using stdin, right? We're using stdin. We can do something like while not end of file stdin. That should be actually it. Let me see if we can achieve that. It was as simple as that, actually. All right. So it also gives you this really weird question when you don't have anything, but I guess that's okay. Yeah, I don't think we need a better solution here. Yeah, it's a first try. So is it 15? Yeah, make BDB exit on Ctrl D. Yeah, let's push that right into the repo. That's right. And let's create a pull request. The yak has been successfully shaped. So I also want to check that Windows also builds. Oh yeah, so I was actually modifying the builds. So I was introducing this build folder, right? And since we build on Windows with Microsoft Visual Studio, I had to modify this bat file, right? And the way I was modifying it was really weird. I was doing like literally batch processing where I would make the changes, push them to the GitHub and just observe the CI, fail or not. And furthermore, I wanted to observe the like what kind of files were created. So at the end, I would have like this debug output that basically prints the current, yeah, typical situations, fucking classic. I would have like dir here, then I would do cd build dir, then cd bin dir, then cd slash examples dir, and maybe it was unnecessary. I just realized I could have just did tree. Like, I haven't used Windows for a while. Okay, so I could have just go to the build and just do tree. Yeah. Well, I'm glad that I started to explaining that, because otherwise I wouldn't remember that there's a tree command. Tree! A tree! I'm sorry. Yes. Oh, and also some of the changes I was able to test by doing this, because I have Wine, and in Wine you can just do Wine CMD and you can just test something. But the problem with Wine, by the way, it doesn't have a tree command. I don't know why. So it does have like dir. Does it have edit? Doesn't have edit either. Notepad. It does have Notepad. That's actually pretty cool. Yeah, but it doesn't have tree. Maybe tree is something that has to be installed separately. I don't know. But yeah. I also forgot that here there is a tree on Windows. I use it only on Linux. Is there a tree on Linux? Wait a second. Okay, can I install it? Can I install tree on Windows? On Linux, I mean. You need to install it. Too lazy to scroll. I'm gonna just assume that it exists. And I'm gonna try to install it. Okay, cool. It does exist. 103 not upgraded. And I'm also using Debian Stale. Think about that. I'm using Debian Stale and I have 103 packages not upgraded. That's how lazy I am. And I also haven't replaced my battery. So yeah, my life is a mess. I know. So tree. Oh shit, it works. That's actually super cool. I like that. Nice. Maybe I'm gonna start using it, because sometimes it's really useful for like debug output in CIs. Here and plots. Look. We fixed a very important bug in BDB. So instead of while one, we're doing while not end of file stdin, because without that change, yeah, without that change, it's just sort of fucking crazy. I'm not gonna lie. But I mean, it's not that big of a deal. It's just like, you know, it's something that I didn't expect. So if I go to the examples, yeah, it's just fucking goes crazy. Love it. /s kind of works as a tree replacement in Wine CMD. Wait a second, ready? Wine CMD. Oh, it's actually recursive, right? So let me see. And what does it do? Oh, okay, it's basically recursively. Okay, thank you so much. Dir, what is that? They don't even tell you all of the possible. This is something that I like don't understand about Windows and stuff like that. Like, I ask for help. Could you give me like the full help, or maybe there is a help dir? Maybe there is additional flag. God damn it. Anyway. Wine CMD WT. Well, I mean, I was actually modifying CI, and I needed to modify this bat script, right? So, and to modify the bat script properly, I needed to check some of the things in CMD, because I don't really use CMD, and I don't want to load Windows. So I just wanted to check that make dir works properly and some other stuff. So to test these simple things out, WineCMD is actually quite useful. Right. Basically. Anyway, so this one is good. So essentially what we're doing, we're shaving the yuck. Nice help, yeah. Cool. The yuck has been successfully shaved. Actually works on Windows, don't know why I didn't. Oh, okay, so it's not a Windows problem, it's more a Wine implementation problem. I see, makes sense. I don't know, maybe they didn't bother to implement like full documentation for this thing. Who knows? Okay, so let me fetch the latest stuff. Windows user exposed. Yes, you got them right. Okay, do I want to rebase 105? Actually, I'm not a big fan of rebasing because it's a very destructive change, right? So what I'm gonna do, I'm gonna just merge master back into the branch. So this is how we're gonna go about that. Just like this. There we go. So and now we have the latest bike yak shaving. I actually confuse this concept all the time. Alright, so what I want to do, I want to go through all the examples and just run them and sanity check them, right? Just simple sanity check. Bin, it's going to be BME, doesn't really have to be this way. BME, and the input is going to be 123F. You said that you have Windows on one of the laptops. Try booting QEMU. That's an interesting idea, but I don't want to do it right on the stream, by the way. I have the Windows on this particular laptop. Will it work? Wait, will it actually work? Because theoretically it should work. Holy shit, this is... Wow. Holy shit, this is so... Wait a fucking second. With KVM, probably it's gonna be decent. Yeah, with KVM it could be actually decent. Oh fuck. Okay, I'm gonna try, but not on the stream because I'm already this stream consumes too much resources, and virtualizing Windows is gonna be even worse. But yeah, thank you. That's actually a pretty cool idea. I do have Windows on my second SSD, and I want to try. What about video drivers? Yeah, that's an interesting point. I was playing game this way when I was too lazy to reboot with pass-through on my GPU. Oh my god, holy fuck. Who needs like an actual Windows in 2021, am I right? You can just, keep it like that. Alright, so another example. So we have also alloc, I think. Okay, alloc is correct. And also print bits. That's cool. So then we have cast. I'm not really looking for correct values, I'm just looking for like sanity, right? It's literally just a sanity check. So E, then we have a Fibonacci examples, cool. Gray code, so that's a gray code. Hello. I think the next one was lerp, that's a pretty good lerp. Then we have a memory. Okay, so this is just a memory dump, cool. Then we have a Pi computation. Oh, okay, so Pi computation actually failed with the stack underflow. That's actually pretty cool that we managed to catch that. Oh, this is because the main is located in the correct place. Okay, so let's actually quickly fix that. So essentially what we're doing here is we introduced like an entry point to the file format. So now you should be able to set an entry point with a special directive. Right, so you set it to something and it gets baked into the program and it will start with a particular entry point. And this is needed because we're gonna have like additional functions in the natives here in the standard library, and having functions here may offset any of the entry points here, so we cannot rely on the program starting from 0. So we always have to specify where it's going to start. But every time I reboot to hardware Windows after booting it under KVM, it does a bit crazy, making every device as new with a lot of pop-ups. That's actually pretty funny. All right. So let me recompile everything one more time. So pi is okeg. Example, and we're gonna have a rod13. Hello world from rod13. Okay, so everything works great. Alright, that's actually pretty pogue. That's pretty pogue. So here's accumulator. And fix pi example. Cool. And I'm gonna push that right into the repo. So I think I want to merge this already, even though 105 is about translating print f64 to BOSM, but I still want to merge it into the master because I think this is a pretty significant change that needs to be merged as soon as possible. So let me create a pull request. So we introduce entry point to the BM files, and I'm gonna just. Oh wait a second! I forgot to check something very important. BOSM to WASM, BOSM to NASM. I mean. Wait a second. We definitely need to implement BOSM to WASM. We definitely need to do that at some point. Holy shit. Imagine me speaking and actually coming up with a good idea. I think it's some sort of like my subconscious was trying to tell me something using my speech section of my brain. We're not gonna do that right now, we're gonna do that later, but we need to actually, like, you know, make an issue about that. BOSM to WASM. Holy shit, this is gonna be a pretty good title to clickbait Zoomers. We definitely need to do that, but I also want to assign it to myself, just in case somebody will try to implement it. So I want to have all of the fun of translating BOSM to WASM, I think. Also, WASM to BOSM would be also interesting. Okay. I think it's possible. WASM to BOSM should be also interesting. Yeah, imagine like taking a program like written in C, you compile to WASM, and then you compile it to BOSM. Well, it's kind of, it could be interesting, like project to undertake, but yeah, we'll see. Compile C with LLVM to BOSM and then translate it to BOSM. Yeah. All right, introduce entry point. Yeah, what I want you to do is I want you to test how entry points are taken into account with BOSM to NASM, right? Because I think they are not taken into account. Yeah, they are not taken into account. And the way we do that, actually, here's the start, right? So here is the start, and it just starts, right? So that means it's gonna be broken. Welcome back, old man. Welcome, welcome, welcome. Okay. So yeah, right now the ASM instructions are completely broken, and we need to take that into account. 105. Cool. And something doesn't. Okay, shit doesn't even compile properly. I wonder why. So what is that? Ooh. Drop is not okay. That's cool. This is because, yeah, on the CI I'm actually compiling x86-64, but only for Linux. So that's actually cool. All right, so the thing to fix that is gonna be go to natives and remove all of that stuff from there. You know what? I'm gonna actually remove drop on the drop. Okay, and that will make it compile. So let's do x86-64. Okay, red is not implemented. God damn it. Let's remove red then. Cool. So now, if we take a look at the examples, fib, fib awesome. There we go. So this is where it starts, right? This is where it starts. And where is the start? Oh. Yeah, there we go. So this is basically, this thing is essentially from a standard library. So this entire thing was put in front of the program and corrupted the whole program. So the program is not going to compute a Fibonacci sequence anymore. If we try to run it, well, it kind of technically computes that, but well, yeah, so you essentially can, well, you can potentially corrupt it here. So what we need to do here, we need to look at the entry point and set underscore start at that entry point. Right, so that's what we need to do. We need to make BASM to NASM take into account the entry point concept. So let's quickly do that. So we're not gonna print f start anymore, right? We're gonna do it like so. If I equal to BASM entry, you know what? I'm gonna do it like that. If I equal to BASM entry, we're gonna print start at that particular place. So I think that's gonna be cool. And if we take a look at the resulting Fibonacci example, or Fibonacci ASM, and yeah, the start now is here. So you have some shit before the start, but nobody cares about it, right? So it was just, you know, put here. So now the actual program will start at underscore start. At underscore start. So yeah, I think we did it. I think we actually did it. Cool. Yes. But we don't really need that garbage in the standard library anyway, so I'm gonna just remove it for now. And yeah. 105. Make BASM at entry point support for BASM to NASM. And we're gonna push that right into the ribbon. All right, so that should be okay. That should be okay. So let's wait for continuous integration. And once continuous integration is done, did I push anything? So I don't see this being reflected in the UI for some reason. Do I have to actually refresh a page, the page in 20? Yes, I had to actually refresh. What's the point of having all of these reactive frameworks that automatically update everything if still in 2021 I have to refresh a fucking page? What's the point of slowing web down if it just doesn't work? I'm too old. So let's do the shit. JavaScript, yes. Alright, so this is how many changes we made, and let's just merge that. Wait. It doesn't need to close this. Okay, no reason to close anything because it's not finished yet. Reacting on request, yeah. Cool. So yeah, that is pretty cool. Now we have entry points and everything supports them. Origin master. Cool. So now we need to start translating our algorithm our algorithms to BASM. So essentially, my idea is go to the natives, and re-implement everything related to printing, right? Everything related to printing in BASM, right? So essentially, we only need write native function. We don't need anything else, only write native function. Everything else here can be just re-implemented without it. So you see what I mean? I think that's gonna be cool. So let's get started. I'm not sure about like alloc and free. We don't really use them anywhere. So if I try to remove them, right? Yeah. I don't know. Okay, let's start with something simple. I'm gonna try to re-implement print U64. U64 is easier to re-implement because you don't have to handle negative numbers, okay? So that's the reason why it is easier to implement. How are we gonna do that? Well, that's a good question. We need some sort of a memory. We need like a chunk of memory that is reserved specifically for printing numbers, and we need to somehow enforce all of the programs to not touch that piece of memory, especially things like ROT13, because ROT13 hard-coded a lot of memory positions, which is not nice. But anyway, so we're gonna have print U64, and it's gonna be a return. There we go, it's gonna be a return. Now, how are we gonna print it? So maybe I'm gonna just go to a print. Oh yeah, finally I can change my title. Programming in my assembly. Lip bosom. Yeah, maybe. I'm not sure how I'm gonna call it, to be fair. Not sure how I'm gonna call it. Okay, so we have print int. So I'm gonna start with the print int. It actually takes a negative into account, so I'm not sure. But yeah. So what we can try to do, so the input goes through the stack. So on the top of the stack we have an input, so we have X that we're trying to print. So what we need to do here is we need to divide this X. We have to take mod, right? So that means we have to duplicate 0, right? That will push X on the top of the stack. We duplicate that. Then I do mod I 10, and that takes a mod. Why do I have mod I? Do I have mod F? Oh, that's interesting. So because maybe at some point we're gonna have mod F. But mod F is more like a library thing, but whatever. Mod 10, so this is basically what we have on top of the stack, and now we need to print that somehow. So this thing is gonna be, yeah, we need to add 0, right? So I need to push something like this, and it would be nice to have a character support. Do we have a character support issue here? Character don't support escape characters. Okay, character. Speaking of yak shaving, I want to have a character literals. Chat, can a developer have a character literals? I want to have a character literals. Is that another yak shaving? Yes, it's not a yak shaving. So supporting character literals is actually easier than supporting string literals, because in case of the string literals, you will have to add them to the memory, so you have to, you know, keep track of them and stuff like that. In case of character literals, you can treat them as literally as numbers, like an alternative way of writing a number. Do we have a yak shave counter? Okay. I don't know. So what exactly we're counting? How many times I went into like a yak shaving mode, or how deep I went into the yak shaving mode? Like how many layers of recursion? What about non-ASCII characters though? What about them? So right now I want to have a support for this thing. Right now I want to have like this one. If I implement that, using non-ASCII stuff means that you can just put something like this here. So, I mean, implementing only ASCII support does not contradict that in the future we're gonna have UTF support or something. Like, it's just, I don't see any contradiction here. I think it's okay. We need to create a recursion tree. Yeah. The yak looks like a gray pig on my screen. Okay. So what I want to be able to do right now is I want to be able to do this thing. Once we have this thing, we can think about, okay, how can we extend it to support Unicode or something in the future? So whatever, it's not that big of a problem in my opinion. It just could be done incrementally. Shaving a yak. Oh. I want to make another cup of tea, but I'm running out of tea. Oh shit. I'm sorry. Sorry for what? Our daddy taught us not to be ashamed of our yak, especially if it's shaved and all, you know. That sounded more wrong than expected. So, yeah. Emojis and Buzzum. Yeah, we'll see. I think this is the last Yulong Max T. Okay. Maybe not last. There's still a little bit of left. Yeah, Yulong, running out of Yulong. That's it. I completely ran out of loose leaf tea in my house. Completely. But I still do have like tea bags. That's their kind of. Need to go outside. I mean, yeah, I guess I need to go outside. It's just like I cannot go outside after the stream because it's gonna be too late. So, but to be fair, it's even better because I try to not drink tea or any caffeine after the stream, right? Because I need to sleep. Alright, so let's actually go ahead and add support for character literals, like very simple character literals or something like that. So that means I'll have to change the title of the stream yet again because people are gonna do this is not assembly, this is C. Okay, so for those people, let's actually go ahead and change the title yet again. Okay. Instead of programming in my assembly, I'm going to do improving my assembly, right? Cool. And I'm going to put character literals, right? And just in case somebody knows what that means. Anyways. Have you seen how tea bags look inside? It's revolting. Well, tea bags look inside. You mean the content of the tea bag? It looks like dust. It's yeah. It's literally just dust. It's like a powder. Okay, but because of that, it has a like a higher surface area, and that's why it actually steeps faster than loose leaf tea. But yeah, but the quality is actually questionable. Okay, so let's do a character literals. How about that? I'm gonna go to the master, and I'm gonna create a branch 120, and let's think how we can add character literals. Character literals. Floor sweepings. Yeah, that's what it is. It's literally them. bm.h. So Buzzum translate literal. Okay, so this is what we have here. So what we're trying to translate here is essentially, first we check whether it's a string. Then we, if it's not a string, we try to parse it as a number. Another thing we can try to do here is if sv count greater than 2 and it starts with this character here and it mother flipping ends with the same character here, that means it's a mother flipping string literal. Right. Cool. So what we can do about that now? Yeah. Yes, it's a smiley. So if sv count -2 is not equal 1, we instantly should return false, right? Because it's not a correct string literal. It is not a correct string literal. But then, what we can do, once we verify that it's a correct string literal, we can return word U64, I think. So we take SV data, so the first character is quote, the second one is that thing, and that should be it, believe it or not. Okay, I guess that's it. So yeah, let's check it out. So data conversion from character may lose sinus. Okay, so let's do uint 64t and return word. Oh, it doesn't have to be like that. Oh, we can make it one of those, you know, buy for points, like set the title of the window of the streamer spending 69 points or something like that. We can make it one of those things, right? Probably, I don't know. Would you spend 69 points to set the title of the streamer's window and get streamer banned for violating TOS? Would you do that? Yes, sounds like a pretty epic content. Dab. Third time the charm. Go ahead, third time. You can do it, I believe in you. Alright, so the thing is, if I'm gonna do if I'm gonna do like 3, I'm gonna check 3. That means it will try to interpret it as a string and try to interpret it as something else, and so on and so forth. This one is just gonna be faster because it's not gonna check too many things. Are we live yet? I'm not dropping any frames, and my ping is okay, but the chat is disconnected. Okay, so I'm gonna go to the Discord. Can anyone tell me in the Discord, is the stream okay? Is this stream okay? Hello? Is the stream okay? I suppose... Okay, so something with the chat, I presume, or maybe something with the Chatirina. All right, so oh my god, stream was okay. Cool. I suppose Chatirina is dead. Okay, Chatirina is dead. Nice. Can I actually put Chatirina somewhere here? I cannot, because it just does not allow me to just have this stuff like this. God damn. Wrong keyboard 2021. I don't know what you're talking about. Sorry. Okay, so maybe we're gonna... Yeah, let me go to here. To the dashboard, maybe. And I'm gonna pop out the web chat. Does web chat work for you guys? Does web chat work for you? Maybe it's Chatirina that is being Chatirina. I clicked on the wrong thing. Oh my god, Twitch is so painfully slow. Holy shit. Oh. Oh my god. Oh shit. Oh fuck. Oh. Fucking so slow. Stop being so slow. Fucking React applications. Okay. Alright, so connecting to chat. Oh, even web chat doesn't work, or does it? I cannot connect through the web chat. Chatirina works fine, but okay, not for me. Like, neither web nor chat work for me. So is it only me, or is it for everyone? I don't know, I'm asking you, because like some people say that Chatirina is okay and everything's okay, and it's apparently only me, or... Yeah, this happens on several occasions. Banned? Banned for what? Excuse me. Everything's okay. Alright, so chat is okay. Well, but I cannot use it. I literally cannot use it. Okay, so we can try to use the Discord then, but the problem is that we cannot easily use the Discord. Alright. Okay, I'm gonna close the chat arena and so I need to split this stuff like that. So I can put it like that, but unfortunately this is not particularly convenient. In Discord it's not like possible for me to have it on the side because it's too huge, right? It has these two panels and there's no way for me to remove them. Right, so I cannot just remove them, but chat is actually very important for what I'm doing here. Okay, so that means I'm gonna just have it like that then. So chat arena, yeah. There's nothing I can do. There's nothing I can do. Member list. What is? Oh, you can click on member list. Okay, cool. But what about the list of the channels? Is it possible to get rid of that as well? Is it possible to get rid of that? Because it's still like kind of meh. Left one is not removable. Why is it so dumb? Holy fuck. Alright. Compact mode, but compact mode saves space vertically, right? If I understand correctly. It saves space vertically, but this is literally an opposite of what I'm trying to do. I'm trying to space horizontally, so it's not gonna help us in any way. Yeah, so there's no like literally way for me to do that. Thank you, Twitch. Very fucking cool. Like what? Okay, so I'm gonna try to pop up the chat one more time. And this is not, it keeps connecting to the chat, like it just cannot connect. Like it can, try to say something in Twitch chat. By the way, try to say something. Oh, can I say something? Just say something. Did you say something? Okay. So, still couldn't see anything. Alright, so it's useless then. Okay, thank you so much. We can try to continue like this then. We can try to continue like this. I don't have enough screen space. Holy shit, oh my god, I'm so annoyed. Multi-billion fucking company cannot even develop a simple fucking website. Alright, so what I was doing, I don't remember what I was doing. Does anybody remember what I was doing? I was doing like a string, like a character literals, right? I was developing character literals. So let me see. And the thing is, people don't even know how to join this chat. Like majority of people are so pepega that they will see, oh, how do I join the Discord? But they won't even see that there is like a Discord link down below. So you literally have to just walk them through like very simple concepts all the time. A bit of an effort, but maybe worth a try. Like, how is it gonna help me anything? Chat Arena doesn't work. It uses the same API as Chat Arena through ARC. So web chat doesn't work. Like, what's the point? Chat doesn't work for me. Anyway, this is just gonna be another waste of time for me. Whatever. Chat Arena uses WebSocket? Wait, what? It doesn't use the IRC? Wait a fucking second. What? Why doesn't it use IRC? Why? That's really strange. Okay. We spammed links to the Discord server chat. Okay. Holy shit! Like, what the fuck is going on with the modern world? Okay, everyone can send the messages. Okay, just trying to make sure. Alright, whatever. Okay, thank you everyone for helping. Let's continue. So, yeah. That's how we're gonna develop right now. Apparently, this is how we're gonna develop. So I'm gonna actually keep Chatterino on the side. Now it works! Thank you so much. Thank you so much, fucking Twitch, for just wasting like 20 minutes of my stream and losing so many fucking viewers. Thank you so much. Holy shit. For fuck's sake. Why am I still using the... I mean, I know why I'm still using this website, because there's like no other place with established audience, of course. And I keep fucking abusing that. Alright. So, I introduced the character literals, right? So we introduced the character literals, and let me see what we can do here. Monty Addicts, you literally have no idea what you're talking about. Okay, so let me see. I want to introduce like a some sort of a test. Chars bosom. Include examples, natives. So it's gonna be Hasm, and we're gonna have an entry point, and the entry is going to be main. All right. So I wonder how we're gonna do that. Push 0, push 1, push 3. And we definitely need a support in terms of syntax highlighting for the extension. Right, that's definitely something that we'll need to have. Alright. Examples. Did I rebuild everything? Chars. And characters were also built. Nice. BDB. BNBDB. Chars. Bosom. Yeah, chars BM. Okay. So I'm gonna break on the main, and running this entire thing. So push works, I suppose. And it returned. And can I inspect the stack? That was weird. Where's the 32? Excuse me. Did I? Oh yeah. I'm an idiot. It's just... Yeah, overall it works. So we have a character literals, by the way. We have character literals. I wonder if I have like something like this. Is it gonna work? You know what? What if we try to implement the Terry style character literals? You know what I mean? So essentially, you have 64-bit numbers, right? So that means you can fit 8 characters there. So let's actually allow up to 8 characters in here. Why not? I mean, yeah. So the same way TempleOS actually does that. And it's actually not that difficult to implement. So I'm gonna show you how you can implement that actually. It's super dumb. Like, I mean, divine intellect. Is it gonna be divine intellect? I don't know. I'm not sure how useful is it gonna be. Like, it could be a little bit useful, but for what? Nah, it's just a waste of time, I think. So because, like, what exactly can you use it for? Unless you want to print these kind of strings, these kind of small strings. Maybe. Then you can even support full Unicode range. Full Unicode range. No, if I'm gonna support Unicode, it's not gonna how it works. It's not gonna be how it works. So no, let's not go there. Let's not go there for now. All right. Add support for character literals. It's actually pretty little support, but it's something that is gonna work for us for now. Also, I wanna extend the editor support. Where is the editor support? Tools, Baza model.l. So I have these groups in here. Jump. Oh, yeah. All right. And how can I have string support? So I remember that I got string support pretty much for free, but I forgot how do you add it. So also another thing, set ft bosom. Do I have something like this? Why there's no? Okay. And if I have something like it doesn't have that either. So all right, I'm gonna create the to-dos. I'm gonna create the to-dos for now. Do bosom vim does not highlight character literals. Okay, and another one is gonna be bosom mode. I'm gonna put it here. To do bosom mode does not highlight character literals. Okay. So this is the additional to-dos. Did I already create a pull request? I don't think I created a pull request. So let's create a pull request. Okay. So let's snitch them up. Introduced in 121. Does not highlight character literals. Okay, yes, that's what I want. Oh, I never actually. Okay, I never actually reported that to do, so that's kind of important. Hello, Rodriadus. Welcome to the stream. Okay, so let me push everything now here. So now we have a character literals. Alright, I'm gonna go to the kitchen, quickly boil up some water for my tea, and then I'm gonna be back and we're gonna continue shaving the yak. Hopefully we're gonna continue shaving the yak. And what we were working on, I think we were working on porting the assembly algorithm to Bosom. This is what we were working on. Yes. Yeah. Anyway, so I'm gonna quickly go to the kitchen and be back as soon as I can. So how much time? Oh, fuck. Alright, let's actually make a small break, actually. Oh, fuck. Oh my god, I'm so... What is going on with me? Small break. 3 minutes. Okay. And, yeah. Let's make a small break, boys and girls, and you guys have fun. Yo, what's up? Welcome back to back. Okay, so I think the IAC has been shaved properly and we can merge the pull request. Too early, I'm sorry for being too early. Yeah. So we can go back to our branch, I suppose. So we have character literals and we can use them to port the algorithm, hopefully. All right. So, and in this branch specifically, I think I can actually fast forward it, so it doesn't need to be like merge or anything. Just fast forward that thing. So let's go to the examples, natives, and we are about to implement U64. Print U64. Print U64 ret, and again on the stack we expect X. That's what we expect here. And the first thing we do, we duplicate this thing on the stack. Then we push, I suppose, 10. So 10. Then mod I means that we're gonna have mod 10. Might as well actually denote it like this. And after that I push 0, so that means you're gonna have this on the stack. Right, and after doing plus I, you end up with plus on the stack, and you basically end up with a character, right? You end up with a character, and the question is, how can you print such character. One of the ways you can print such characters, you can actually print it. Oh boy, oh boy. So since you have a write and write accepts a memory pointer, you need to put that character into the memory, right? Somehow you need to use write 8 or something. Yeah, it's gonna be in a reversed order, so it's one of those problems that we'll have to deal with. One of those problems we'll have to deal with. Reverse order and shit. So maybe we're gonna have some sort of a buffer into which we're writing things, right? And then we're gonna have a separate function like reverse, which reverses the memory, and then we're gonna print that thing. Okay, so yeah, that's very interesting. But the question is, how can, like, where is all of that going to be located? So we need to reserve some sort of a memory, which can be used by the print U64. And the problem with the memory is that string literals right now can literally override that memory. They can literally override it. So what we can do now, we can bind something like print memory and allocate, let's say, 30 bytes. It's dumb, I know, but this is one of the way to do that. Like right now, at least with the current language. So this is basically we allocate the memory like that. That's very interesting. Ugly print number function wants that pushed the number of digits using a register onto the stack and this. It's actually a pretty good solution. This is literally what I do in assembly. I mean, why is that not a good solution? Is it because is it because somebody told you that it's not a good solution? So, this is like everything wrong with the modern software development. Like you have a perfectly working solution that solves the problem, and because of some ideological bullshit being basically pushed by universities, people think it is wrong. This is like literally insanity. You have a solution that you can verify, right? Like literally black box. You have an input, you have an output, and on any input you get a correct output. And it's only wrong from some bullshit ideological perspective that has zero value in software development. Holy shit. Oh my god, it triggers me so fucking much. All right. So, we also need to keep track, in that case, we also need to keep track like where exactly we're gonna push all of that, right? Intellectual masturbating, yeah. That's what it is. So we have a print memory, we have like allocated print memory here and shit. I might as well, before duping anything, so we dupe this stuff. Alright, and then, well, I can push print memory. By pushing print memory, by the way, I'm pushing a pointer to the stack. So that means we're gonna have like a print memory here. Right, and because of that I'll have to duplicate 1 instead of 0, right? Because I'll have to go 1 layer deeper. Right, and so this is what we're gonna end up with. So after that, if I want to do write, so how does write accept the arguments? How does write accept the arguments? Let me see. Write 8. Okay, let me see the implementation of this entire thing. The address is what? The address is the previous value. Okay, that makes sense. So what's funny is that I need to duplicate that stuff. Alright. So I push that, duplicate that thing, prepare everything. Then what I need to do, I need to duplicate one. Right, I need to duplicate one, basically this one, and this is what I'm gonna have here. Alright, but since it's a previous one, I'll have to swap one as well. And I'm gonna end up with this particular thing, and the address is this one. And by doing like write 8, I'll consume both of these things here and increment the memory, right? And increment the memory. Okay, so yeah, after write 8, this is gone, and this is what we end up with. This is what we end up with. Cool. Alright. So the next thing we need to do, we need to actually take x and divide it by 10. So we'll have to do swap 1. Right, we'll have to do swap 1. That swaps this entire thing. Right, and I'm gonna push 10. Right, so that pushes 10 onto the stack. Right, then we do div I. Right, div I. That essentially does that. And we need to end at some point here. So then you have print memory at the top. So we'll need to swap it back. We'll need to swap it back. So, and this is what we're gonna end up with. And we kind of ended up like right here. We kind of ended up right here. What's up, Cozy White Bear? What's up, what's up? So then we'll have to do like a lot of different things in here. We'll have to not only divide this thing by 10, but also increment the print memory, right? We also need to increment the print memory by 1 at least, right? So maybe I'm gonna actually go and put this thing here, right? So this is not gonna be the thing. So after doing write, I want to push 1 and do add, actually plus I. So that will just increment this entire stuff. That will just increment this entire stuff. It's gone. Was gone. I was not really paying attention to the chat. Is everything okay? Hello everyone, by the way. No, not in terms of the stream, but I mean in terms of what's going on in the chat. Is like it's just people are talking about something and I was actually ignoring the chat. No WhatsApp, no signal is my friend. WhatsApp, is WhatsApp dead now? I don't use any of the like mobile messengers at all completely. So I don't know what's going on there. So is WhatsApp completely dead now? It's more spooky now, not dead. Why is it spooky? So is it because it's like reporting some stuff to KGB or something? Oh, it's owned by Facebook, I see. Oh, okay. I see. Facebook is more scary than KGB, that's for sure. Facebook is fucking scary. I do agree with that. It's reporting to Facebook, yeah. So the Facebook is actually one of the things that stops me from having Instagram. Because I was considering to create an Instagram for maybe when I'm gonna learn shaders, and Instagram is actually a perfect place to post shit there, but I'm really scared of Facebook, so fuck that. It's on for a long time, but they want to change policies to report more to home. Oh, I see. Facebook wants to more data from it, more people migrated to Telegram, Signal, and can actually message people there. Nice. So yeah, interesting. It's very, very interesting. Facebook really fucked up their reputation if you think about it. If people actually migrating, like from their products, like they're really fucked up something in terms of like branding, reputation, marketing. It's just really, really interesting. All right, so this is really strange. So we keep track. So I want to kind of start over. Right, I want to kind of start over because this one is difficult. So essentially, we want to keep all of that in this particular order, right? We want to keep all of that in this particular order because it's just how we do that, right? And this is going to be the current state. The state that we maintain is basically the current value and the pointer at the memory where we print in everything. So I don't think Facebook is that evil though. It's evil as Apple and Google. I didn't say evil. I actually worded my words really carefully. I said that they fucked up their reputation. Think about these words. I didn't imply that something is evil or not evil. Categories evil, good is not applicable there. It's just like a very childish categories. Nobody gives a shit about them, okay? So I said they fucked up their reputation, right? So whatever the fuck is that supposed to mean? Anyway. Cool. Evil, good are categories for normies. Now, what if I swap this entire shit? What if I do just something like this? This is not a real grade, it's actually Yulong. Swap one. Okay, so we're gonna start with that. And maybe that's going to be the current state, right? So what if we try to assume that this is the current state? And, oh yeah, so this is kind of interesting. So if I put loop here, right? If I put loop here, it's gonna take the take the name and you won't be able to use it, so we'll have to prefix it. Maybe at some point we'll need to introduce a concept of local labels like in NASM, but for now we can do something like printf. Like prefix all of that, right? Let's just prefix all of this. So this is gonna be our prefix. Now. So let's start with duplicating. So it's going to be dupe0, right? So this is the dupe0. And let me see. So then I'm going to push 10. I wish I could actually... Oh my god, Emacs, you're making me so fucking sad. Something does not react properly, so I'm gonna actually keep the stack somewhere here, hopefully. So we push 10, and then I'm gonna do plus I, right? So this is a plus I, so that gives us plus 10, right? After that, actually I have to do mod I, right? So instead of plus, then I'm gonna do push 0, right? So this is like this, and then plus I, which will just add this stuff together. So this is what we have here, and this is what we want to print. So how we're going to print all of that is Well, that means I'll have to do dupe 1, 2 to duplicate this entire thing here, and I'll also have to swap it, swap 1, right, because that's how it has to be done. And then we'll have to do write 8, which will write this entire thing. I guess that's one way to do that, which means that maybe swapping this shit around was not a particularly great idea, because it doesn't really introduce that like much of the helping. So yeah, it's just like not particularly great. So let me not swap anything. Let's actually not swap anything. Let's actually not swap anything. So if you don't swap anything, you have to duplicate 1, right? Then you push 10 and then O, right? This is what you end up with. And in here, well, this is kind of interesting. You still have to duplicate, but 1. You duplicate have to 1 and still have to swap it like that. Okay, it literally doesn't matter. You end up with just duplicating and swapping anyway, so it's just... Yeah, but at least it's like a natural order here, right? At least we saved up on a single instruction, so you do that and then you just do write. Cool. And after that, I want to do push 1, right? And then I do plus I, and that gives me plus 1, right? So I'm updating the memory. Then I need to swap 1, which does that, then push 10, which does that, then div I, which does that, and then we can swap 1 back again, end up with this thing where you have a memory on the top, and we completed this single cycle, right? We completed a single cycle. Cool. After that, I want to duplicate 1, which gives me this thing. And what I need to do here, I need to check if it's equal to 0 or not, if it's, you know, if it's 0. So the way I can do that, I can push 0, right? Then I can do equal, which will end up in this condition, and maybe I'm gonna do not after that, so this is gonna be not, and then I can do jump if true to printf 64 loop, and that will basically finish the cycle. So that's how it works. So this is the whole thing. Well, Anaboth, hello, welcome to the stream, Anaboth. What's up? What's up? We're programming in our own custom assembly. Yes. This one is really interesting. Yeah, so it tries to take the memory and print it on the stack. And the question, okay, so once we finish this loop, so this is the loop that basically fills up the memory, right? It fills up the memory. And again, we're gonna probably end up at the end of this stuff with print memory n and x equals 0. That's what we're gonna end up with. So somewhere here down below. All right. And what we're gonna even do here? Oh, wait a second. I think I can do pretty cool shit. Right, look, this is the loop, right? This is the loop, and I can probably just indent it like this to indicate that this is a loop. There we go. And it's still a valid bosom. It's a still valid bosom. It's pretty cool. And after that, I may try to call write, right? I may try to call write. But another thing that probably makes sense to do here is to add a new line, right? So because we're supposed to be adding a new line, how can we add a new line? We can push 10. Our character literals do not support this stuff. So we're gonna push 10, right? And maybe I have to duplicate 0 first. I need to duplicate 0 first. And then push 10, So, and then by doing write 8, I'm doing this thing, and then I can do push 1, write n, and then plus I, and that does plus 1 like this. Cool. So I added a new line. The next thing I want to do, I need to write the memory. So to do that, I'll have to use the native write function. So native write function, it accepts address as the previous argument and the count as the at the top of the stack. So if our top of the stack looks like this, that means what we have to do, we have to push print memory, like this, right? Swap them around, swap 1 like this, and subtract them. So you're gonna end up with something like this, right? Which essentially means you're gonna end up with something like this. And now you know the size of the buffer. Right, now you know the size of the buffer. After that, you can push print memory one more time, print memory, and what you ended up with is the at the top of this stack you end up with the memory from which you have to print, and then the count, and what's going to be the order. Okay, the address has to be actually below the count, so what we have to do swap 1, and this is the memory that we expect, and then I'll have to do native write, and that will essentially write the string from the memory, and it will consume these top things. And after that, we still have this garbage on the top of the stack, which we can just easily drop, right? We just drop in the garbage in the stack, and there we go, the function has finished. Right, so this entire function, it just takes a number and tries to print it. It basically first prints it in the memory, right? And then it takes the memory and gives it to the write native function that will print it in an actual system, in an actual native system. So this is the whole algorithm. And it's not that big of an algorithm if you think about it. It's a pretty straightforward, simple algorithm, but now we need to test how it works. By the way, to not break things, I think I'm gonna just do it like that. Maybe not. Anyway, so... fuck. Let's put underscore here to indicate that it's a new function. Yes, it will end up reversed. The code is not finished! Okay, so sh. Alright. Now, let's create an example that tests all of that. And I want to actually try to do all of that in a debugger. Try to do all of that on the debugger. Print U64 test bosom, right? So what we're going to do here, we're going to include examples, natives, hasm, and then here's the entry point. We're going to push 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Also, let's actually, put 0 here. And then I'm going to call print U64, and then I'm going to halt, and the entry point for this particular program is going to be just main. There we go. So that should be okay. So that's the whole test I want you to have. Alright, so if I try to build this entire thingy, Majingi. Oh yeah, it has to be underscore. Thank you so much. Yeah. So print U64. Cool. So let's go to the build and to the examples. Bin BDB print. There we go. So yeah, here's the IP. We can clearly see the IP. And let me break on main. There we go. We're breaking on main. And let's run fibxz. What do you mean? Is that something wrong? I don't know. So, oh shit, I just realized that we don't have a way to inspect the memory in the BDB. Oh well. I see in your... Yeah, it is like that. Yes, there is .exe. What's wrong with that? We need a way to inspect the memory. So we can try to inspect the stack or something. Okay, so wait, what? Call... Okay, so we go in, went into call 1. So this is the return address, by the way. This is the thing that we have. Then we duplicate it. What did we exactly duplicate? Oh, stack is actually... Oh shit, you know what I forgot? I didn't take into account the return address. So that's actually quite important. Because on the top of the stack, what you have is... Yeah. You have a return address. You have to take that into account. So that means you will have to swap 1 first, right? So you swap 1, so you bring the argument on the top of the stack, right? So, and then you can continue doing that. So that's actually kind of dangerous. So, yep, let's continue. One more time. Break main. Let's run this entire thing. Call 1. And then we're doing swap 1. So after swap, yeah, after swap 1, as far as I can tell, I don't remember where is the top of the stack. I don't remember where is the top of the stack. BDB C. So if I do stack dump stack, we use BM dump stack. And when you use BM dump stack, how do we iterate them? We iterate them from left to right. That means that the bottom is the top of the stack. Okay. Right. And that actually swapped this entire stuff. Alright, so then we push 0. And there we go, it was pushed. Then we push 10. Why did we push 0? Excuse me. Okay. Alright. Oh, okay, so now we have 48. Alright, so I really want to be able to inspect the memory. Seriously, I think inspecting the memory is kind of important here. So let's try to shave off that yuck yet again. Are you guys ready? Are you guys ready to shave off a little bit of a yuck? Because I'm flipping ready. But before we're gonna do that, I need to commit whatever we have. Initial implementation of print I64 in bosom. Right. So yeah. So where is the memory inspection issue? Because we really need to inspect the memory, like be able to inspect the memory. Memory, so there's no way to examine the memory in BDB. Okay, so let's actually work on that. Chat is minefield, but not dead. What do you mean by that? So, alright, so let's go back to the master, and it's gonna be 85. So bdb.c. Alright, so how are we going to inspect the memory? So we have run program, stack, instruction pointer, and we can actually do something like this. Memory, inspect the memory, /n. Alright, inspect the memory, and it's going to be below instruction pointer, right? It's below instruction pointer. So I'm gonna put it like that. Let's break. Inspect the memory. All right. So the question is, how are we gonna accept? Like, we need to accept the arguments there, right? So we need to accept the argument. B accepts the arguments. So here's the input SV, right? So we can trim this entire thing. So it's very interesting. So we may try to do something like that. So if you want to inspect the memory, you will do something like M then you would use print memory, so you should be able to use labels, right? And also you provide the size, like 10, how much you want to actually inspect there. We might as well also accept like X. So and the question is, how are you going to print it? Are you going to print it like a row, or are you going to print it in hexadecimal? So that's a good question. Maybe we're going to introduce, I'd imagine it working something like M count type, where it's kind of like GDB. Oh, I see. So maybe it's going to be like in GDB, who knows. Is it really like, but we're doing in the style of BDX or whatever that's supposed to mean, but I don't know. So that means I would be able to do something like M69X, right? So it's gonna be hex, print memory, right? M69X, that's what you're suggesting, I suppose. For now, I think if we're gonna go GDB route, I'm gonna just put X. So I could implement it like that, but that means I'll have to change the way we parse arguments, right? So right now, how we parse it is we have a character, and on top of that, we have like input SV. So, and we can parse the rest of the input. It's just easier to parse it like that right now. But maybe later we can implement it like differently. All right, so memory, location. So we have an input SV, and then I want to trim it, right? I'm trimming it here. And maybe I want to reassign it. Do we use it afterwards anywhere? I don't think so. Yeah, we just read input buffer, and then we do it like this. So there's a control world in here. Control word. I see. Oh, we could actually extract it from the control word then. Interesting. We could extract it from the control word. But I think it's easier to do it like that. So here's the input SV, or yeah, input SV. Oh shit. Chop SV, chop by delimiter, and what we can use here, we can chop this thing like that, but that means we'll have to actually save it somewhere here. So it's going to be input SV, right? It's going to be like this, input SV, and this is the delimiter that we're using, right? Hopefully, and that should give us the location, right? Location, or maybe we're gonna call it where, sure. And then we're gonna have a count SV chop by delimiter, input SV. We don't really need to actually do that. It's gonna be like input SV then. There we go. So we have a where and we have a count. Cool. So now we need to print all of that. So we had a function that translates the label or address. So we have a BDB parse label or address. Let me see how it does that. So it accepts address and outputs address here, right? Essentially, it looks up the address or the label or whatnot, and this is essentially what we can use here. So let me go there. Right. So where is M? Or is it called X? Yeah, there we go. Okay. So we have state, and the state is called state. Cool. So the address is going to be where, the address is where, and the output is going to be somewhere here, inst address. Let's call it just address. So it's initially 0, and that thing gives us this stuff. So if I need to learn how to handle the errors here. So how do we handle the errors? If it's equal to BDB fail, right? If it's equal to BDB fail, right? We are printing cannot parse address or label. What's interesting is that it would be nice to even say what exactly you mean here. by doing something like svfmt, svarg, and what exactly you're trying to parse, right? So we're trying to parse where here. And then we do continue, right? Can parse address or label, and we actually explain what exactly we're trying to parse, and we couldn't. Cool. So the count. We also, I know that this function is also used at sv to u64. So yeah, let's go back. The count is gonna be something like this. I want to rename where to sv to indicate that it's, you know, not a number, and this is also sv, and this is where, and this is also where, and uint64t count is going to be what? Sv to u64 count sv. There we go. So maybe we're going to do that actually after we try to parse where. So there we go. We have a memory address and we have a count how much we want to put there. Isn't that amazing? I think it's goddamn amazing. Okay. So furthermore, maybe we can also try to parse label or address. So do we want to accept labels there as a count? We may actually, it could be actually useful if you think about that, parse label or address, because maybe the size of the memory that you want to inspect could be in a label. So it does make sense to do the same thing here. I think it does make sense. So that's why we're going to repeat this entire shit here. So but initially is going to be equal to 0. But instead of where, we're going to have count. So there we go. Count. Cool. So here's where and here's the count. And we probably also need to check that the count doesn't go over available memory or shit like that. But I'm too lazy to do that right now. Anyway. So for maybe while. Okay. It's gonna be int address, inst address I starting from 0 while less than count plus I, and we're gonna be doing printf 0 to x space state bm. And I don't remember what do we have here. BDBH. Where is the? So here's the BM itself, and then we take a look at the memory of this thing at where plus I, and I guess that's it. I guess that is it. So we can also check if this thing is less than BM memory capacity. There we go. Now we can do printf. Cool. Is it gonna compile? It doesn't fucking compile, mate. Why doesn't it compile? So it doesn't compile in this particular place because svarg where is not a sv. Okay, so let's actually fix that super quick. There's another one. Too many arguments. Yeah, I see. I see why would you say something like this. Something BDB, go back to monkey. Reject humanity. Okay. Where is it? I lost my shit. Where is it? Here it is. I just want to finish this shit already, please. It's not that difficult of a problem. Chat, are you okay, by the way? Is everything okay? Because you're really dead today. So hopefully everything's okay. Is the chat okay? Okay, so everything's okay. So, now, I'm not dead. C. Sure. Yeah, now we have something that can potentially, you know, look into the memory. And the thing we want to explore here probably ROT 13, right? So let's take a look at ROT 13. All right, so let me take a look at H. Inspect memory. Okay, cannot parse address or label. All right, so I can start at 0 and show me first 5 bytes there. There we go. So here they are. We can see first 5 bytes in here. Yeah, that's pretty pogue. I'm not gonna lie. That is pretty pogue. Yep. So we can even try to provide more, like 10 of them, and yeah, that should help us to inspect some like memory and stuff. So this is like a very rudimentary way of inspecting the memory, so later it can be actually improved and shit, of course. But yeah, for now I think it should be good enough for us. And if I've introduced basic way to inspect the memory in BDB, and let's push that right into the repo. So we're shaved a lot of yak today, not gonna lie. So no, this is not what I wanted. Excuse me. This is what I wanted. Right. So we're gonna close that 85 in here. And of course it's kind of Papago, but so for usability problems we can have separate issues. Alright, so that was pretty straightforward. So once we have that, we can troubleshoot or just debug our implementation and see how it fills up the memory, right? So that's gonna be the idea. Fucking love relief. It seems there is a problem with high DPI displays in that case. App windows appear smaller. Solution is just moving a bit the window and it should get scaled automatically. So essentially the scaling parameters are calculated on some sort of event, and that event is not sent at the beginning. So, but it's sent on moving, so you have to move the window, right? And that will trigger an event where it's going to be recalculated. I won't solve that bug, just move your window around until it fixes. Well, I mean, the library is open sourced, so maybe, I don't know. Welcome to open source, I suppose. Is everything okay? Why is it still building? Any tips on writing Ethereum prover? Yeah, sure. Just write it. So yeah, that's the best tip I can give you. If you want to write Ethereum prover, fucking do it. You have my blessing. Cheers. Why is it still building? Why? Please don't split up my VOD. Please don't split up my VOD. Hello, refresh the page. Refresh the page, otherwise you're gonna have huge delay. And nobody wants a huge delay, trust me. The Twitch is gonna split my VOD. Oh my god, it's gonna be such a huge pain in the ass to upload on YouTube. fuck's sake. I don't know what is going on today. It's really strange. And it really demotivates me and just puts me in a really bad mood right now. So I have no idea how to continue streaming. I'm really sorry. So yeah. Alright, so introduce basic way to inspect the memory. So I already merged that. Hopefully that will yeah, so that already closed the issue. Okay, so let me go to the master and fetch the stuff. Okay, so did it fetch it? I think it fetched it, and I'm gonna merge origin master, and I'm gonna remove that one. Okay, so in this branch, right, in this branch, let me see. Alright, so I'm gonna actually merge the with master. Alright, so to synchronize everything, and finally I have this stuff here. Was it too loud? Holy shit, I'm sorry. I'm so sorry. I know that it probably was too fucking loud. Shit. And it was okay. Okay. Alright, I'm sorry. Okay. Okay, let's do this. BDB, and what I want to look into is the example of print test. Okay, cool. So we can try to inspect the memory, right? So I'm going to do X, and we're starting at print. Oh, it doesn't show me. Do we have a way to look into the all of the labels, list all of the labels? That would be actually pretty cool. Okay, I'm going to print memory. It's not print actually, it's X print memory, right? Really? Is it really how it's gonna go? Print test. Okay, so in the natives, it's called print memory. Okay, X print memory, and then I want to print 5 of them, and it doesn't support that. Okay, so why doesn't it do that? What are you asking? Build examples, print memory. Here it is. Did I forget to rebuild everything? I don't think I forgot to rebuild something, but we can rebuild it several times, sure. Okay, it's read the symbols, loading the debugging symbols, everything looks okay, and I'm breaking on main, I suppose. That's one of the things I want to do, and I want to print the memory at print memory, and show me 5 of these things, and it cannot parse the print memory label even though it is available right fucking there. Did I fuck it up so badly? Whatever, so maybe I fucked it up so badly. Right, so it's gonna be 0, and I can do something like this. Okay, so it's filled with 2A, right, which is probably the ASCII code for the star, right? It's ASCII code for the star. Let's try to run this thing and maybe see how it goes. Okay, next one. So we call that one, so we can take a look at the step. We're swapping things around. We're duplicating things. Right. So push 10. The next one is that. Plus I, S8. Then we duplicate, then we swap. And we are about to write to the memory. So we can do something like X05. And we are about to write to the memory. So we just wrote to the memory. And if I took a look at the memory, we have 30. And what is the 30? I suppose 30... is the internet okay? Okay. 30 is in hex. It's 0. Perfect. So that's exactly what I wanted to have. Nice. So let's continue. So we do plus I. And that incremented the current address. Then we're swapping things around, so we brought the value here, we brought the value here, okay, whatever, and we divide everything, so that decreased the value of this thing, right? Then we duplicate the previous thing here, I suppose, right? Push 0, check if it's equal, if it's not equal, right? And we're about to jump to the beginning and repeat the process. Okay, so we keep repeating the process. So far so good. So far so good. Now, chat, if this person will ask something about hair, please issue the hair command, okay? Because I don't have time to explain anything right now, right? Okay. Yeah, it's a very new, fresh and new take. Okay, thank you so much. Cool. So let me see. Will I be able to? Yeah, so I think so far like a single iteration actually went really well. A single iteration went pretty well, and I think I want to stop somewhere here. So let's call it something like print after loop. Let's call it after loop. Right, so this is where I want to basically break and shit. Okay, cool. Breakpoint set at 22. I'm gonna start running this entire thing, and there we go. So here is where we ended. And let me see. X0, and let's print like 10 numbers here. And this is what we have. We actually have like 30, 39. Oh yeah, that makes sense. Yeah, because it's reversed. So we have you have all of that in the reversed order. So we can actually go and do like more, 15. So yeah, it filled up the memory. So I actually implemented the algorithm correctly. It fills up the memory, but it's like in reversed order and shit like that, right? So yeah, potentially this may work, but what we'll have to do here now, we'll have to like write more shit into it. It's gonna be like 15. At the end we have a new line, right? Then push 1 plus 1, so to increment the memory and shit. Then swap 1, and then we call a native. A legal memory access at 32, instruction native 7. Huh. Wait, what? Error illegal. It's a BDB thing. Wait a second. It's a literally a BDB thing. Illegal. Wait, what? Illegal memory access. Why? Oh, access. Why is it an illegal memory access? All right. So I think I fucked up the after loop situation. I think I fucked up the after loop situation. I think I fucked up the after loop situation. I wonder how. So I dupe 0 push. So essentially. So yeah, I also have to. I don't take into account the return address. So this is actually quite important. Let's actually try to go one more time through all of this. When you start executing this entire thing, right? When you start executing this entire thing, so you end up with the following thing. So we have X, and on the top of a stack, you have a return address. So the first thing we do here, we actually swap them. Like this. So this thing is on top of the stack, and then we push print memory. So this is what you end up with. Here's the print memory. Okay, dupe 1 duplicates X, then you push 10, then you do mod 10, right? Then you push 0, and you do plus 0. There we go. So you end up somewhere here. So then you do dupe 1, right? This. Then you swap like this. Then you write 0. Right, then you just write 0. Cool. then you push 1 and increment this entire thing. Then you swap 1, right, swap 1, 10, divide everything by 10, swap 1, dupe 1, 0, check if they're equal, check if they're not equal, and then jump. And this is how you perform like a single iteration here. There we go. So this is the single iteration, and at the end here, you're gonna end up with n and 0 here. That makes sense. So in after loop, you're gonna have print memory plus n, and this is a 0. Okay, so this is a single iteration. This is nice. Dupe 0 duplicates this entire thing. Then you push 10. And that writes to the memory, if I remember correctly. So the write 8 expects an address here and a value here, I think. If I remember correctly, of course, I might be actually not remembering that correctly. So instruction write 8. So let's see how it's implemented. So it expects. So this is the address. Address is the previous one. Okay, that makes sense. And that consumes both of these things, right? And it writes at the end of the address the thing there. All right, so then we push 1 and we add +1 here. Then afterwards, I push print memory one more time, swap them around, and I subtract them. Maybe I don't have to swap them, by the way. Wait a second, that could be a mistake. So binary op. So in a binary op, I take the previous one. Okay, so that's the mistake. I found the mistake. So you just have to push the memory and don't swap it, and then you do minus, and that subtracts the memory from here, and you end up with just n plus 1, where +1 is the new line. After that, you push print memory, just give press memory, then you swap 1. And then you do write, and write expects this thing to be a memory and the count how much you want to write. All right, that consumes that. Then drop consumes that, and the last address actually returns also consumes that. There we go. We finished the full cycle. So the mistake was swapping here. Okay, so we found the mistake. Cool. So that algorithm should work now, hopefully. Let's recompile everything. This is such a fun assembly, not gonna lie. I don't know, it's so fun, like following and maintaining the stack and just understanding how, you know, stack transforms. It's so fun. I really like programming this assembly. I know that I'm biased, but I think it's just super cool. All right, so let me see. And after that, I'm not gonna try to do BDB. I'm gonna just straight up go to the for the BMA. There we go. Here it's. So yeah, we implemented like it's reversed. I know that. Okay, it's reversed. But now let's implement reverse. How about that? Let's implement reverse. So first I'm gonna do a committee. All right, it's gonna be implement print u64 underscore. Oh, actually, fix. I think we fixed it. Fix print u64. And let's push that right into the ribbon. Native std reverse. We don't need to have it native. It could be yet another function within the standard library. Right. So let's implement reverse. So initially, what we're going to expect here, I suppose we are expecting, it's going to be the same interface as write. So it accepts the size of the thing you're reversing at the top of the stack, and then the address, the base. So it accepts base and count. Right, but what's interesting is that you push base and count, and then you do call, and you're going to end up with the return. So this is basically the stack that you have to deal with when you enter reverse. Right, so that's what you have to deal with. So before doing anything, I guess you would have to do swap 1, 2, right? Swap 2, which will basically swap return and base, and will put return address at the bottom of the stack, so you can focus on base and count. All right, so you can focus on base and count. All right, so that's very interesting. And here we can start the loop, right? Here we can start the loop. Reverse loop. There we go. And it's gonna be like jump if reverse loop. To be fair, I think we should check the condition. We should check that count is not 0 at the beginning of the loop, right? So will be Bosom standard library mostly written in Bosom? Yes, yes, it will be mostly written in Bosom. So the only thing that we'll need native is syscalls that interact with the operating system. So we're gonna have a read syscall, write syscall, and everything else is gonna be primarily implemented in Bosom. And the reason why it has to be implemented in Bosom is because it will make it easier to port this standard library as we introduce more and more different platforms, like for this language that it compiled to, right? So this code will be compilable to x86-64, and once we add compilation support for ARM, this code is also going to be compilable to ARM. So once we have ARM support, we don't have to re-implement it in ARM, we just compile it to ARM. So that's pretty cool. Okay, so where's my stack? So I need to keep maintaining the stack. So this is the base, this is a count. So maybe I also want to do the following thing. So swap 2, and then I'm going to do swap 1 to actually bring the count like here. So I essentially reverse the whole stack. Cool. So, and the next thing I want to do, I want to duplicate this 0. Right, I want to duplicate this the current element. So you don't even need a translation layer, right? What translation layer? Do you know what we're doing, by the way? You may want to check out the project that we're doing. I hope you checked it out. So we're developing a virtual machine, and virtual machine has its own bytecode and it has its own assembly. So yeah, this is the assembly for our virtual machine. So right now we're working on a compiler that takes the bytecode of the virtual machine and translates it to x86-64, right? But we also have an interpreter that doesn't require any compilation. So, and we're just translating some of the functions that we implemented in assembly to our assembly, so it's more portable. Anyway, so I duplicated this thing, and then I'm gonna push 0. Right, so it pushes 0. And what we need to check here, I think we need to check EQI, right, and after that it will check if it's equal to 0. And we're gonna do jump if reverse loop end if it is equal to 0, right? Right, if it is equal to 0, and a reverse loop end is located here. So, but then here we're gonna have unconditional jump. This is the so this is where we perform the check, I think. So 101. Okay, so here's the reverse loop. Here we check this if it's equal to 0. If it's equal to 0, we jump to the loop end, and this is going to be the body of the loop. This is going to be the body. And this is where we're going to actually swap things around. Cool. But yeah, after that, if we check that, we're going to end up with the count, base, blah, blah, blah. So, and after the loop, by the way, what we need to do here, we just need to drop the count and drop the base and drop the base. Damn it. And then once we drop them, we're going to return out of that. So we need to focus on the body, right? We need to focus on the body. Why don't you put comments with the stack content just inside the Bosom code? I already tried to do that. It's too much effort jumping between the place where I'm writing code and between the place where I'm keeping the stack of the code. Okay, so now. I need to be able to swap two values, right? So I wish we had a function, something like swap8, right? So when swap8 is going to basically accept address A and address B and just swap the contents of these things between them. I think that's a reasonable thing to have. So the way we're going to approach that is the following. I'm going to dupe 1, which will bring the base at the top here. Then I'm going to... So this is the address of the first thing that I want to increase, right? So then I'm going to dupe 1 probably one more time, right? So that brings that here. After that, I probably want to push 1 and subtract it, so it's going to be minus I, so that means I'm going to have minus count minus I here. After that I'm going to do dupe 1, which will bring the base here, and then I'm going to do plus I, which will have base plus count I. There we go. So I have this thing and this thing here. So essentially the characters that I have to swap together, and then I just call swap8, another function that is not implemented yet. Another function that is not implemented yet, and that function is supposed to consume both of these values and swap their contents. So there you go. It was as simple as that, believe it or not. Alright, so then I'm going to push 1, right, and then minus I, and I'm going to end up with minus 1 here. Then I'm going to swap 1 like this, then push 1 and plus I, it's gonna be like this, and then I'm gonna swap 1 yet again. Cool. Then I jump back to the reverse loop where we check the condition and repeat this loop over and over again. There we go. That's the whole thing. That's the whole reverse here. That's the whole reverse. Cool. Does it compile? Should be compiling. It seems to be compiling. Cool. Swap8. Swap8. This one is interesting. So this is what we have here, right? This is what we have here at the top of the stack. But we're also gonna have return, right? So we're also gonna have return. So here's the swap. And of course, like, first thing we probably want to do is to swap. So this is 0, 1, 2, swap 2, which brings the thing here, and there we go. We have two addresses here. All right. So, then I probably want to duplicate 1. Right, I want to duplicate 1. Duplicate 1, and that will duplicate this thing. And if I duplicate 1 yet again, that will duplicate this thing. So basically I have the copies of this thing here. The copies of these things here. So we should probably use some sort of like a read8 instruction, which reads something, which reads from the address on the top of the stack, right? Which reads from the top of the stack, read8. Right, so let's go somewhere here. So just, yeah, it accepts like a single argument and literally reads a character from the top of the stack. So, alright, so that means if I do that, this is what I'm gonna have. Then I can swap 1, and this is what I get, and then I can read 8 one more time, and I'm gonna end up with A. Interestingly enough, I can try to now 0, 1, 2, dupe 2, this gives me that. Then if I swap 1, I end up with that, and that is perfect for write 8. So it's essentially at address B, it will write A. So that gives us that. Cool. Now I can try to do dupe 2 one more time. That gives me that. Then swap 1 one more time. It's gonna give me that. and then write 8 is gonna do that. Cool. After that, I can just drop all of these things together. And then we return from this function. Cool. Could we probably implement it more like simpler? I think. Okay, but what do we do in this case? What do we do in this case? All right, what do we do in this case? What do we do in this case? Compile error. So you do realize that by doing a compile error, you just force the programmer add additional space. Why? It's the only difference in your solution is just single space. Why? Okay, let's actually see. Let's see what we can have here. So this is a swap, and this is a reverse. Okay. And cool. So I forgot to use it. The next thing. So here we have print memory. We prepare everything though. It also consumes. So reverse actually consumes everything, right? So then we swap everything. So I think we can do it like this. So we're gonna do dupe 1 and then call the reverse, right? Then call reverse. So that reverses the memory, and then we can just write it. Cool. And it kind of worked, but not really. Because we have to reverse them before we're pushing a new element there. So yeah, we have to reverse them before we push a new element there. Okay, all right. So what was the current state? So this is a swap. So let me see. So the stack is going to be like this. Value, you have ret, you swap them around, and then you have a print memory, right? So this is what you have at the end of the loop, right? This is what you have at the end of the loop, but essentially you have 0 here and plus n, right? So what I'm thinking is print memory. Yeah. Oh shit! It's not exactly what I want. All right. So we have to reverse actually upfront. We have to do the reverse upfront. So then we have native write. So we need to rewrite the whole thing here. We have to rewrite the whole thing here. All right. So this is what we have here. So this is a print. Then I push print memory to here. Push print memory to here. Right, then I do minus I, and that subtracts this thing from here. So I get n. Cool. So afterwards, I want to duplicate this thing. So that gives me just n. And then I'm gonna push print memory one more time. Right, and I'm gonna swap 1, and that gives me that. And I think this is how we expect that in the reverse. Yeah, this is how we expect that in reverse. Swap 1, right? Yeah, that reverses this thing, and then I'm gonna call reverse, so that reverse everything. and that consumes that. Cool, we reversed everything. Then I'm gonna push print memory one more time. Here's the print memory. Right, so here's the print memory. And I need to swap it one more time, so that gives me that, and then we're gonna call native. Right, so that consumes that, and then we're gonna do drop. That removes that, and then we return from this thing. Yes, it should. You don't understand what print U64 is needed for. You make too many assumptions. Yet again. Okay, so that completely fucked it up. That completely fucked it up. Did I... so something with the reverse. Did I forget to properly do that? So it's one... It only did it once, what the fuck? Wait a fucking second, so it actually did the reverse once. So yeah, it swapped it. There was 0, 1. Okay, let's try to test the swap, like the swap 8, because I just want to make sure that there's no problem in here, right? I just want to make sure that there's no problem in here. Oh my god, I'm so tired. Every time I get into something actually interesting, I'm already fucking tired and I cannot do that. This is so frustrating, holy shit. Because I have to, like, I need you to shave that yak. I really need you to shave it because, like, I needed to implement all these things to properly check everything, but I'm already fucking tired. Alright. So, let me take a look. What was the example that was using? How is it called? It's called print something. Yeah, this is the shit I'm using. Alright, so, this is the halt. I'm gonna halt this entire stuff. And, let me push the address. We're gonna push 0, and then we're gonna push 10, right? And then we're gonna just write this thing, and then I'm gonna push 0, push 20, and I'm gonna just write at that particular address. Cool. The next thing is I'm gonna push 10, 1. Push 0 and push 1, and I'm gonna call swap, and I just wanna swap 8, yeah, swap 8, because it's already taken. Okay, so that should swap these two bytes, right, in the memory. That's exactly what we're trying to do here, right? So let's try to compile that. We're just trying to swap some bytes in the memory. We're just trying to swap some bytes. So this one is a BDB. Thank you, Twitch. So fucking great. Such a nice stream today. Holy shit. Okay, so break and main. Okay. So run this stuff. So also want to take a look at the memory. So we're gonna start to look at the memory. Okay. Next, push 10, 0, write 8, x 0, 2. It's 1, it's 10, okay, that makes sense. Right, x 0, 2. This thing, okay, that's cool. Then I push and I call this function, right? So right now, before I call this function, it's that. Then, oh shit, I cannot skip until the next return. Oh shit, oh fuck. It would be nice to be able to skip the function calls until return, you know what I mean? Like in GDB, so you can skip the call so you don't have to like go to the function. B funk C, maybe. Okay, but I mean, like, it's too much mental effort for me. All right, well, let's make a small break. I really need a small break. Today is a really rough stream. Can't afford shaving another yak. Well, I mean, the more we implement, the less we have to shave it in the future, right? Alright, so let's continue. So what's the easiest way to do that? So you could probably break on the current call, but you have to break on the call +1, so it doesn't really help that much. So I guess we have to go through this entire function. Why not? Dupe 1? What the fuck is dupe 1? Oh, I'm looking at the wrong thing. Can I... Now what? After swap 8. This is what I'm gonna do. Okay, so I'm gonna recompile everything. So we can always just put a new label there, which is kind of convenient feature. I'm gonna lie. So we're gonna break at main, right? So, and we just do that. Yes. Right. Right. Let's take a look at them. Cool. And if I continue, and also I want to break on after swap 8. Alright. And then I'm gonna continue. And then if I take a look at that, it actually swapped it. So the result is swapped. You see? That's actually pretty cool. So swap works. I know that for a fact. Swap works. That's cool. So there's something wrong with the reverse. We need to figure out what exactly wrong with the reverse. So it also, yeah, it also drops everything. So yeah, it should be okay, I think. Let's actually simulate everything, right? So how do we use the swap? So here is the n, then I duplicate the n, and then I push the memory. So that means at the stack we have push the memory. So I have the count, and print memory. Count and like base and count. So this is what I have here, base and count. And I call reverse, and that gives me return, right? So that gives me return. If I go back to the reverse, we swap 2, it's a 0, 1, 2, right? So that gives me that, right? Then I swap this thing, so I have a count here. So then I duplicate 0, push 0, check if they're equal, and if it's true, I jump to the reverse loop end, right? If it's not, I don't. Okay, so that consumes that. So duplicate 1, that gives me a base here, and duplicate 1 again, that gives me count here, and then I push 1, I subtract 1, right? Duplicate 1 more time. Then I do plus 1, so plus this thing, and this is basically my address. So I have base plus count minus 1, base, and it has to be swapped. So swap swaps that, I suppose, and consumes this entire thing. Then I push 1, and I subtract it. Okay, that makes sense. So I just subtract it. So then I do swap 1, push 1, add 1, and swap it again, and that, then I jump to the reverse loop and repeat the process yet again. I don't see any mistake, unless I made yet another mistake here somewhere. I don't know. It's really strange. Alright, so at some point we're gonna end up here, where count is probably gonna be equal to 0 and base is gonna be equal plus count. So that's exactly what we do here, and then we drop it twice, and then we're gonna return address. So that should be okay. That should be totally okay, and I don't see any problems with that. Yeah. And yet, maybe I call this thing incorrectly, but that's really interesting. One, 0, 9. It's like it moved these two things together. So the original, what was the original number? 1 to 3. So, right, so, and it definitely reversed it like that, right? So it's gonna become 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. And what it did, well, it kind of shifted it. Well, that's by itself is already like too much if you think of it. It's shifted it. So it was. This is not what I wanted. Like what I wanted to swap is effectively this thing, like with that one, and then go even further and swap that one with that one. So I don't quite understand. Because I keep swapping base and base plus count minus 1. Am I doing that? Is that an incorrect way of swapping things? Yes, it is an incorrect way of swapping things, because you're gonna actually have to do that in half. You have to do that to the middle, right? To the middle, right? So yeah, that's completely incorrect. So you have to stop at some particular point. So the counter that we rely on should be completely different. So okay, let me see. So we'll have to probably rewrite it yet again. So print, push print memory, that gives us, so this is not what I wanted. All right, that's interesting. That's very interesting. Cool. All right, so we have a return address first of all, then we have a count, then we have a base. Right, so we have a count, then we have a base. Then. Oh, Nafla, what's up? Welcome to the show. So I do swap 2, so that brings me here. Then I do swap 1, that gives me count then. So I think one of the things I want to do, I want to duplicate this thing, right? Duplicate this thing and divide it by 2. Right, so this is what we're going to have here. So the actual thing divided by 2. And that's what we can use to check whether it's time for us to, you know, exit the loop, right? And the way we check that, we duplicate this entire thing, of course, then add 0, and then we check if it's equal to 0, right? And if it's equal to 0, we jump to the end of the loop. Otherwise, we don't do that. Cool. So the next thing we do duplicate 1. Yeah, so this one has to be actually duplicate 2. So by duplicating 2, you do base, and then another duplicate 2 is going to give you count here. There we go. So this is what you have. You have count, you have base. Then you push 1 and subtract that one from here. Then you duplicate 1, which is base. And then you add this entire thing like that. So there you go. And then you call swap 8, right? Then you call swap 8. And that thing swaps things around. All right. So now you have to subtract both of these things, right? You need to subtract both of these things. Subtract that, add +1 to this one. So that's what we have to do, and we also have to end up with count /2 count base, so with the same order here. All right, so that means I have to remove this entire part and slightly rewrite it. Let's see how I can do that. I'm going to do push 1, then I'm going to do +i, right, and that gives it +1. Cool. Next thing, I need to do swap 1. By doing swap 1, I'm doing this thing. Then I do push 1. Wait a minute, it has to be -1. -i. Push I, -i. So, and that gives me -i. And I swap 1 again, bringing it back. Then I do swap 2. Push 1 plus I. Swap 2, and that gives me +1 here. There we go. So this is how we do that. So this is very interesting, actually, believe it or not. So I wish I have an energy to explain you. So imagine that you have a local variables in the call, right? So you have variables A, B, C. So imagine that you want to increment C by 1, right? You want to increment C by 1. The address of that local variable is 2. So if you want to just increment C by 1, what you do? You do always swap 2, then push 1 plus I, swap 2. So essentially that gives you always like C +1 without changing the stack. So essentially you, by doing swap 2, you bring C to the current top, modify it, and by doing swap 2 again, you bring it back to its original place. So essentially if you want to work on B instead, you replace this entire thing with 1. And you can actually go as deep in local variables as possible. So you can just have like n variables on the stack, and if you want to modify nth variable, you can always do that. So in the future, I'm thinking actually, if we're gonna have some sort of like a sophisticated assembly, not assembly but preprocessor on top of the BASM that allows me to write macros, I would probably wrap that into some sort of a macro like this. Define local n and maybe some sort of a block, right? So, and then I can do something like that. End, right? So, and in here I can use n, and then I can put a block here. So something like that would allow me to maybe do something like local 5, right? And just maybe modify the current variable like this, like push 1 plus I. So, and this is basically the block that indicates that I'm modifying the local variable 5, and then maybe I can even like bind a to 5 and completely forget about this kind of stuff. So in this way you raise the level of abstraction of assembly even further. And seems it's pretty easy to optimize it later. Yep. So you see where I'm going with all that. That's actually super cool. So yeah, speaking of whether I want to have a language which you can build starting from assembly, this is pretty much the direction I want to go. Right, so you identify the pattern, and then you have a powerful enough of macro system that allows you to abstract away that pattern. So yeah. But all of that are just dreams, so it's not like something very... Yeah, so my idea is to have assembly with a very powerful macro system to the point that I can build my own high-level language starting from assembly. And that assembly could be some assembly for a virtual machine, why not? So I don't mind that. Jiayang, what's up? Welcome to the stream. How's your... I almost said, how's your cock? How's your prologue and cock education? That would be a really strange thing to ask. Yeah, hello, what's up, okay, good. So I do push 1, and then I swap that. How is my cock? Thank you very much. Okay, I see. Alright, let's try to compile this entire shit. And it doesn't even compile. Unknown instruction. Okay, that makes sense. Alrighty. So, okay, after that, after I modify this entire thing, if I take a look at this stack, that we have in here, right? So that's what I'm gonna end up with, right? So this thing is gonna be 0, this one is gonna be actually half, and this one is gonna be actually plus of the half. So instead of dropping it 2 times, I have to throw it 3 times. You're doing okay. Okay, cool. Really glad to hear that. So, and once all of that is dropped, we return. So we're actually implementing this tiny library of BASM. So in BASM, you're gonna have print U64. Yeah. So this is interesting. Print U64 is not gonna be a native function anymore. It's gonna be fully implemented in BASM itself, and it's also implemented in terms of other useful functions, and all of that is gonna be part of this tiny library that you can use. So swap 8, for example, swaps like 2 bytes in memory that you want, and we're using that to implement a reverse, and then we're using that to implement print U64 because it prints it into memory in the reversed order, and then you want to reverse it back. Yeah, so that's how it works essentially. Yes. That's pretty Todinpong. Yes, that's pretty Pogue. Node Gineloi. Alright, so let's try to compile that. Everything seems to be working, everything seems to be working. So if I try to execute that, it didn't work. It didn't work. Fuck me. Okay, so what if I don't reverse this entire shit? Okay, so I push memory minus I and get n. So I then get n. Alright, so what if I try to get rid of this entire thing? I just want to make sure that the problem is in fact in the reverse function, right? Just I want to make sure that it's that. So I'm gonna do that, then I swap that, and then I write that, right? So that should give me the confidence that the problem is in that function. So the stack underflow, okay. So we end up with that, so I subtract that, and that means I have to push this thing one more time. Come on, come on. Okay, so this is correct. It's just in reversed order. That's cool. I'm happy with that. Nice. So in here, I'm trying to do the following thing. I might as well actually do it like that, and right, just swap it like that. Just prepare it for everything, and just remove it from here. Okay. Still works, right? And essentially, instead of doing this stuff, I could have just dupe 1, right? So just doing dupe 1. So you have these two arguments in the stack already. You duplicate 2 elements there, and yeah, then we just consume all of that, and it is not reversed correctly. Okay, so reversed is fucked up beyond repair. That's nice. Cool. One more time. What can I say? So essentially what we have here, we have n, so we have n, then we push print memory one more time, and then we call a reverse, right? Then we call a reverse, and that gives us a return. So reverse, there we go. Swap 2 swaps these two things. Swap 1 swaps these two things. Really? That's actually fucked up. Wait a second. I think I found an error one time. Alright, so initially, after doing that, you have n on top of the stack. Then you have memory. And then you swap them together. And that way you call reverse. Right, you call reverse. And that gives you return. You swap them like this, and you swap that. Okay, so I made a fucky wacky. Then you do 0, then you divide it by 2. Cool. We duplicate the 0, check if it's equal to, then jump to the end if it's equal to. Cool. Duplicate 2, so that means we duplicate this thing, and then this thing. Then push 1, subtract the 1, duplicate 1, and then sum them up together. Right, sum them up together. Call swap, which consumes this entire thing. Push 1, subtract the 1. Swap 1, subtract the 1, swap back. Swap 2, swap 2, push 1, plus 1, swap 2. Okay. Where did I make a mistake? I literally don't see it. Is it because... fuck. Well, I mean, if we have odd amount of elements, we're just not gonna touch the last element, so that makes sense to me. Yeah, so then... Really? I don't see any mistakes here. Seriously. Then we jump in here. Then we, like, when we're done, I just drop all of them, and here is the return address, and I return from that return address. So that makes sense. Alrighty. Sorry. Yeah, okay, so it's very interesting. And it just doesn't do the trick. So let's take a look at the print U64 after loop then, and maybe start debugging from there. So it's going to be PTP. Oh shit, it's all broken, PTP. Right, and let's break on after loop. Alright, so let's run this entire thing. Let's take a look at the stack. So this is the stack. So this is the address, I suppose. Then we're gonna be doing -i. Right. So the next one is gonna be -i. What does it give us? It gave us 10, so that makes sense. Then we push 0, right? So and then we swap that. Then we duplicate that one more time, and this is where we start. So these two things are relevant to what we're doing, so we need to print 10 of them. We can also inspect the memory, right? Inspect the memory, so here's the memory. We know that there should be 10 of them. Okay, so let's continue. Streamer, stop what you're doing and explain me everything in detail from scratch. Otherwise, I won't be able to help you. Ah. Oh shit, people. You're always swapping with the last element. So with n-1, n1 with 2 minus 1. So are you pointing out in my mistake, or you explain how I have to do that? I don't understand. You always swap in with the last element. So 0 with n-1, 1 with n-1. Oh, okay. Yeah, your mistake, okay. But I'm subtracting n as well. I'm subtracting both of them all the time. So I'm incrementing the base and I'm subtracting the count. I have to subtract 2 from the count. Is that the whole thing? Holy shit. My god. Jiang, do you plan to apply for Google or something after the university? Holy fuck, you're so smart. Like, how can, like, you have divine ability somehow to look at the stream and grasp the whole context of what's going on and actually come up with a solution. Holy shit. That's amazing. That's really amazing. Yeah. Not everyone like can do that. It's just super fucking amazing. Thank you so much. Yeah. Knurr decides, yeah, he's a fucking genius, seriously. Alright, so that's exactly what it is. Okay. So after we reversed everything, right? So after we reversed everything, we have the n. So we want to like put. Do we want to have the second right? I think that's what we want to have. We want to have like a second right. So let me now push. Yeah, we can do something like this. Push 0, push 10, write 8. So that writes the end symbol, right? After that, we can actually drop. So what are we dropping here, actually? We're just dropping the last number, I presume, right? So drop that, we push that, and then I push 0, push 1, and then I do native write. So that will create, that will essentially print a new line. All right, so let me do that. Okay, so now we implemented print U64, as you can see. So here's a print U64. So essentially, in your example, you can do the following things. You can do push 1, 2, 3, and you can just call this thing 3 times, and that will give you this result in a reversed order, of course. Right. So, and this is not a native function, by the way. This is not a native function. This function implemented completely in Bosom. Right. So, and that's my goal. So the only native function for printing I want to have is write. Everything else should be implemented in Bosom. And if everything else will be implemented in Bosom, it will be super easy to port all of these functions in the future. Right. Hopefully, of course. I'm not sure. We'll see. Yeah. So that's pretty pogue. That's pretty pogue. So now I want to like get rid of this native function and maybe port everything to using print U64, and we'll see how it goes. Let's see how it goes. Okay. And we don't even have a dead code elimination when it comes to you know, translating to assembly. So all of this garbage that is not used is going to be included into the final one, into the final assembly file. Yeah, oh my god. Delete trailing white spaces. Cool. So this is the Bosom. Do I want to commit that one? I don't think so yet. Okay. All right. Reverse the output of print U64 underscore, and I'm gonna push that right into the repo. We're pushing that right into the repo. So let me just think. So this is a really stupid way of allocating memory, actually. So. This is a really stupid way, but yeah, what we essentially do here, we're allocating some memory for for the printing. So to make sure that whatever memory you allocate in your program is gonna go after this entire thing, right? It's going to go after this entire thing. Okay, so I want to actually put it to do a better way of allocating memory for standard printing functions. Okay, so this is going to be the to-do that I want to have. All right, so let me take a look at what we use. Where do we use print U64? So it's going to be grep print U64. This is a really dumb way of doing that, of course. Or n. Okay, so we have it in a cast. Alright, so when I cast things, it's not that particularly interesting. Okay, we use it in a gray code. That's pretty pogue. Which means I can try to do call U64. There we go. Cool. So let me see if it's gonna compile in case of the gray. So this is U64. Oh my god. Cool. Alright, seems to be compiling. And let me try to run the gray code generator. And gray code generator actually worked. Look at that. So yeah, and the printer for the that is used by the gray code generator is actually implemented in Basm as well. So that's pretty cool. I'm not gonna lie. Huh. That is so cool. Test and replace all U64 printers. Yeah, that's what I plan to do actually. So the way we're gonna do that, I think we're gonna go to the natives, and I'm gonna just comment it out. All right, I'm gonna comment out this thing, and that will break the compilation in all of the programs where we use print U64. So, and let's see how it's gonna go. And yeah, unknown binding print U64 in the cast. So let's actually go to the cast. And I'm gonna basically replace this entire stuff. Call underscore. So we use that in 2 places. So another one is in the bits. Okay. Query replace that. Cool. Nice. So I guess that's it, I suppose. We can now do the following thing where I go to the natives and just maybe remove this entire thing completely, and probably rename print U64 to just this. To be fair, maybe such functions shouldn't be called print U64, maybe they should be called dump, right? Because they are primarily made for debugging, because we already saw confusion in chat. Some people were asking whether such function should print new line, because they didn't know what we use them for. We should call them dump, in my opinion. Yeah, we should call them dump. All these functions are just dump function to test things out there for debugging purposes. Yep. So that's why it's gonna go like that. Alright, so let's go yet again here. So I'm gonna quickly replace this thing with dump U64 like this. Cool. Hello, Programador Binario. Welcome. And yep, boom. Cool. Nice. There's also in bits. Replace. Yep. And in that one as well, of course. But I'm not sure if I want to have this like test function here. It's just so dump U64. Yes, I'm using Vim today. Streamer pronounced Spanish Portuguese really well. Well, because I'm Russian. We share a lot of sounds. So some people like English speakers, like native English speakers, usually say that Portuguese and Russian sound the same. And it's true unless you speak either Russian or Portuguese. So, and I suppose the reason why for foreigners they sound similar is because we share a lot of sounds, right? We share a lot of sounds, and we have a similar pacing when it comes to saying things. Russian speaking Spanish, yeah. Programador Binario. Did I pronounce that correctly? Probably not. Anyway. I don't even speak Russian that well, to be fair. Like, I think I'm generally don't speak well. So yeah. Bilingual problems is when you start speaking both languages like shit. Alright. Nice. Portuguese. So what we're gonna do here, I wanna... Hello, I'm from Ireland. Hello. Which one though? I'm sorry. I'm Spanish and I have never thought Portuguese and Russian sound similar. Yeah, probably. Yeah, I'm sorry. I'm sorry. It's just a joke. Just a joke. Okay. I'm just a dumb Russian. I know nothing about political situations in the world. It's just, yeah. So can you print hello? Yes, I can. Believe it or not. So it's gonna be like this. So BME, and we do have hello here. Would you look at that? Hello. Isn't it epic? So the way it's implemented, by the way, we're allocating hello world here, right? We're allocating hello world here, and we're pushing it, we're preparing the memory, we're preparing all of the arguments, and then we use a native write call. We're literally using a native write call, and there you go. So, and you're not Russian. Yes, I'm Canadian, sure. Well, I mean, Jiang is smarter than me, that's for sure. I can assure you about that. Alright, so let me see. He's probably less experienced than me, but he's definitely smarter than me. Thought you were Swedish. No, I'm not Swedish, I'm sorry. What type is that bosom? What do you mean? That's a very interesting question. What are you doing? I'm programming in assembly that I invented myself. How about that? I'm not just programming in someone else's assembly, alright? I first wrote my own assembly and I'm programming in my own assembly. How about that? The assembly flavor, strawberry. I don't know, I just made it myself. Like, what kind of flavor do you want? Like, it's my own assembly. For my own virtual machine. And since I am the creator of that assembly, I hereby declare that the flavor of that assembly is strawberry. That's right. That's official. That's a canon. This flavor is strawberry assembly. Right. Anyways. What's gonna be the next thing? So, did I actually strabism? Yes. I wanna commit that. Okay, cool. Completely deprecate print U64 native funk. I'm gonna push that right into the rip. And it's probably not going to compile because on Linux we're also trying to build this entire stuff, right? We're also trying to yeah, there we go. A non-binding print U64 for test what the fuck? Excuse me, this is not what I expected. Did I actually commit this thing? I thought that I deleted it. Okay, buddy, okay, so I don't think I need that. I don't think I need that. Okay, so, yeah, read 8 is not implemented. Okay, so the reason why the examples that we're compiling before not compiling anymore is because they also need to compile the standard library. Hello bosom self-modifying code. No, you cannot have self-modifying code in bosom because the program is in a separate memory. It looks like it pushes n into the byte hello world, the first byte of the code. Well, what do you mean by self-modifying code? If modifying memory is a self-modifying code, then yes. But for me, self-modifying code is when the code literally takes and modifies its own instructions that then gonna be executed. So yeah, by that definition of the self-modifying code that I use, you cannot modify it because the virtual machine implementation of the virtual machine specifically forbids you to do that. Well, yeah, so a virtual machine has 3 sections of the memory. It has a stack, a completely separate section of the memory, the program instructions, absolutely different section of the memory, and the memory itself. Right. Hello world, this string hello world, located not in the program section of the memory, not in the stack section of the memory, but in the static section of the memory. And that static section of memory is specifically designed to be modified, if that makes sense. All right, so let's make our things compilable to assembly, to an actual assembly. So we need to implement the read8 instruction. Streamer, is that project open for PRs? Well, yes. First of all, I would suggest you to read the contribution rules. So here are the contribution rules. Second of all, I think I should mention that in contribution rules at some point, but I'm going to mention it right now. The issues that are assigned on me, please don't touch them. That means I want to implement them myself, and I probably won't accept any pull request from anyone to these specific issues. Second of all, if you want to do something that is not listed in the issues, you can try to do that, but there will be high chance of me rejecting your pull request because you will try to introduce something that was never even discussed. So generally, I would suggest you to first create an issue and wait for my response so we can discuss that. Another thing, if you find an issue that is not assigned to me and it doesn't have any description, don't try to assume what needs to be done here. Please ask first, and I will provide what exactly needs to be done here, because you may actually potentially end up implementing something that is not actually what's needed. So, and hence your pull request will be rejected. So, yeah, so like general information. So, but apart from that, apart from these things, it's open for pull request, yes. So if you had a byte after hello, it would be modified, replaced by new line. Yes, it will be. Okay. Let's implement read8 instruction. So read8 instruction is supposed to take the pointer, in the from the top of the stack, right? From the top of the stack. So let's actually read the pointer from the top of the stack. So we're actually starting to generate assembly, right? From the top of the stack. Yep. And then so but the top of the stack doesn't actually point at an actual pointer unless we subtract the word size. Yeah, so I need to actually bring up to speed. So what we're doing right now, by the way, we're trying to make our bytecode compilable to x86-64 assembly. We have a special translator that translates that bytecode to x86-64 assembly. All right, so the next thing, I suppose I need to save this entire thing into, let's say, RDI. Maybe RBX is going to be okay. Maybe, I don't know. Maybe Rex. So here's the top of the stack. Then I take this thing and then I move it to Rex. Right, so the value will be in the Rex. After that, I want to actually read this thing into the top of the stack. So in Rex, we have an address. Actually, we have an offset to an address in the static memory. But we don't have a static memory itself. Okay, so that's very interesting. We don't have a static memory itself. So one of the things we'll have to do here, we have to add support for that static memory. Alright, so this is probably how we have to do that. I'm gonna outline all of the instructions that are not implemented yet. So this one is gonna be printf 1, 2, 3, 4. It's gonna be to do read 8. So this is one of the instructions that needs to be implemented here. So another one is gonna be write 8. Right, so that's another one. Another one. Okay, so this is gonna be like that. So another one is gonna be drop. Should be also pretty straightforward to implement. I think it's super simple. Can I implement it like that right now, because it's literally decrementing the stack pointer or something? I guess I can do that a little bit later. To do drop. Okay, what I'm trying to do here is just I'm trying to make it compilable. Oh, return. Return is going to be very interesting. Are you in Python? Yes, I'm programming in Python right now. I'm literally programming in Python. Do you like Python, by the way? Python is my favorite language. Look at how expressive it is. It's actually super expressive. Yep, it's just amazing. I'm not gonna lie. So that's another instruction that needs to be implemented. Alright, printf 1, 2, 3, 4 to do the I. So I especially like that how the amount of jobs, like high-paid jobs there is for Python is just fucking amazing. I think Python is such a good investment in your career. So, and that's exactly why I actually learned it. It's fucking amazing, not gonna lie. I'm wet because of Python programs. Well, I've been wet for the 5 hours already. So, okay. Cool. Another one is gonna be call. This one is very interesting. Print 1, 2, 3, 4 to do call, and we'll have to implement all of that to make it compilable on to x86 64. All that stuff must be implemented. Printf to do GMP. Because you break stuff when he gives you another error. Yeah. So essentially I have a program for which some of the instructions are not implemented. I'm just going through the asserts and I mark these instructions as to implement, right? Because I don't really know which ones I need to implement. To do mod I. Cool. I was like, that's what the fuck? I've never seen that syntax in Python. Well, welcome to the coding stream. Alright, so what do we have? A supportive function call. Alright, so this is the third one, and if I take a look, yeah, so this is the third one, and for the natives, write is the 7th one, so we'll have to do it like this. Else if inst operand as use69 equals 7, we'll have to do printf native write, and it's actually going to be to do native write. And I forgot to add new lines here. It's very important. Alright, seems to be good. Let me double check some stuff. New line, new line, new line, new line, new line, new line, new line. Cool. So we don't even need to implement that many new instructions, to be fair, to have support for all of that. Like we need drop, division, modular, jump, unconditional jump, return and call, and native write. That's it. That's actually so few instructions. That's amazing. Alright, so I'm pretty sure we can implement all of them. So example, and let's take a look at the Fibonacci, maybe not Fibonacci, but 1, 2, 3, F, ASM, maybe I, ASM. There we go. So here are all of these things. It would be kind of cool. Yeah, here are all of the instructions in here. So here is the start, and we just push 1 to 3. So everything before start, by the way, is just a runtime from the standard library. That's what it is. It's just a runtime from the standard library. Nothing particularly special. But maybe we can use that to test things out. So we push 1 to 3, and then we sum them up. And then we just call print i64, but we don't have to call that thing anymore. So yeah, by the way. Oh shit. Well, we just need to make it compilable though. So fib asm. Yeah. So in here, native print. Do we still use print i64 for all this shit? Oh my god, we'll have to do something about it. I'll have to do something about that, but for now... Oh boy, I'm gonna change the example 1 to 3i to actually call print u64. That's what we're gonna do. So I'm just literally calling, and it's actually dump. Yeah, it's actually dump. You didn't see that, okay? All right, build examples 1 to 3i. Awesome. Here it is. So, and call is not implemented, right? Call is not implemented at all. That's a lot of different shite. That's a load of different shite. So the thing is, like, I'm kind of afraid to implement this shit, like, blindly. But maybe that's exactly what we need to do here. And for the Fibonacci example, yeah, Fibonacci example is all positive. Like, I can always just call dump u64 and just forget about that. That's cool. All right. So what I'm gonna have, use dump u64 in 1 to 3i and fib examples. So this is the first thing. Right. So remove redundant example and okay. Outline instructions needed for the dump u64 x86 64 compilation. There we go. I'm gonna push that right into the repo. Okay, cool. What have we got? Now I'm gonna go to the BASM to NASM, and since we're gonna be using dump u64, we don't even need that thing here. Like, we can just literally remove all this shit. There we go. There we go. And oh, well, shit. I didn't want to do that. I just wanted to do again. Yeah. So yeah, because it's gonna be like it's located within that thing itself. All right, let's implement which one? I don't know. Let's implement drop. I don't know. Drop like literally drops the frame on the stack. Right. So that means I need to bring this thing here. To do comment. The to do comment in inst is also to do read 8. Okay. Thank you. Thank you so much. Okay, so I'm gonna bring this thing here, and what I need to do here is I need to now subtract VM word size from it. And after that, I can move stack top back. I guess that's how we do that, right? So I take the stack top, I subtract a single word, and I save it back. So that should be pretty straightforward. So that's the whole implementation of drop. Like, I didn't see any other way to implement that. It's pretty straightforward. Good. Yeah, and if you take a look at the 1, 2, 3i assembly, right? So where do we use drop? We need to probably revert this entire thing, of course. Drop. So here it is. So it takes the stack, subtracts it, and just does that. Do we want to test it out? Probably. I don't know. There's nothing much to test out here. Just drop it. So, for example, these kind of things should be optimized. That's for sure, right? Like consequent drops should be essentially like this multiplied by 2, right? At some point, but we're not working on optimization right now. That's why we sort of repeat this thing several times. So that makes sense, I think. So how can we test all of that? What are you working on? I'm working on a virtual machine. You can find the source code here, hopefully. I think the bot is dead. Yeah, okay, so this is the source code. So, and on top of that, like, we have a virtual machine, the bytecode of which is also compilable to x86-64, and this is what I'm doing right now. So I have a bytecode, and I'm trying to compile it, translate rather, not compile, translate, okay, to x86-64. Yep. So, and it's actually pretty straightforward. Like, I have instructions, and I literally, for like, if I hit these instructions, I just generate, like, speed out this assembly code. And yeah, so the thing I want to do, actually, I want to test some of this stuff. I want to 3 boson, right? So I'm gonna hold in here, right? So I'm gonna just hold, and let's also drop everything. So I push 1 to 3, and then I drop all of them, and let's see how an assembly is gonna look like. So all right. So let's go into the assembly. By the way, did I... okay, so G, by the way, is not enough. I remember that in printf, right, in Sodium printf64. Why do we have so much wall of text in the chat? You guys talking about some sort of engines, blueprints, all of a sudden? I'm not following the conversation, so what are you guys talking about? I'm just curious. Like, you seem to be having like a very interesting conversation. All right, so we're gonna say that we're gonna use dwarf debug format. This format is actually quite cool because not cool. So adding this flag will enable us seeing the original source code in assembly, which is quite cool in my opinion. Alright, so let me rebuild all that one more time. So I'm gonna do gdb 123i.exe. So, and then I can break on start. I'm breaking on the start, and then I can enable, I think I should run it first. And here's the original source code that is generated. So this was achieved by actually baking like the debug information into the executable. So maybe I also want to take a look at the registers. I think registers are going to be very useful. And all right, also I want to take a look at the stack. If I take a look at the stack top, right? So here's stack top. We don't have it apparently. Stack top. Very strange. Even though it's available, but not really. All right. So I can step. ASM and visual scripting coexisting. What? So where is the stack top? Okay, so here's the stack top. Has a known type. Oh, okay, so I had to actually step before. Okay, so there we go. So here's the stack, and then I can convert it to uint64. I think it won't allow me to uint60. Okay, so it has to be unsigned long int, and it has to be a pointer to unsigned long int, and then I can dereference it, and that's the value. that we apparently have here, and maybe we can take a look at like maybe 10 of them. So here are the values of, and I think it's garbage. I think it's primarily garbage. But yeah. So what we're essentially doing here, we're just pushing some stuff. Can I take a look at the display? Oh, stack top. Okay, so stack top by itself is not particularly useful. We need to take a look at the stack. Yeah. There we go. So this is what we have on the stack. Cool. Now I go in even further. So now on the stack we have 1, 2. And maybe it also makes sense to display the stack top. Subtract stack. Can we do something like this? That would be actually pretty cool. Print. Can I print that? But if I convert that to just void, like pointer to a char, I think pointer to a char would be. Or maybe if it's going to be a pointer to long int, and this is also a pointer to long int. Unsigned long int. The differences between them, well, that has to be pointer. Top should be bigger. So I'm not quite sure why this is a negative value. It shouldn't be negative in my opinion. Well, it's negative. All of a sudden. Well, and it's not correct either. Okay. It's very strange. Because top of the stack, I subtracted this thing from top of the stack and it should be 0. Maybe I'm just doing that incorrectly. Who knows? What if I wrap this stuff around? Because I want to treat them as values, if you know what I mean. If I treat them as values, there we go. Yeah, that's very strange. But anyway, I can push things around. And if I try to print the stack top, right, so it's that, and then I'm subtracting it and move it back, and I can take a look at this stack top. Oh, because stack top is the value that is like, okay, I see. I see. Is it doing a pointer arithmetic try? I'm okay. Okay, but all right. So let's prepare the GDB script. Let me create like tools. Right, we already have tools to be fair, don't we? Don't we have tools already? Here they are. Here they are. Okay. How should I call it? x86-64 GDB. Okay, this is how we're gonna call it. So what I'm thinking is I'm gonna break on start. So GDB script mod. So break on start, and then we run it instantly. Enable the TUI, and also enable the assembly. So this is what we have here. Another thing we need to do, we need to start displaying the stack, right? So we need to start displaying the stack. And take a look at the stack top. So actually just a stack, and I convert it to unsigned int long. So this is the pointer, and then I dereference it, and I'm gonna say that I want to take a look at like 10 of them. So I don't really care about more than 10. So the next thing is that what I need to do, where is the pointer arithmetics? So stack top, I have to dereference this thing, right? I have to dereference this thing first of all, and that is a value that I need to treat as a pointer to long int, right? And only then it may give me the correct value, but not necessarily. So the value itself is rather complicated. It could be like this. Yeah. So stack is a pointer. We convert it to this thing, then we dereference it, and then I want to cast it back to the pointer because its value is a pointer. But by the way, it's not necessarily has to be like that. I could just treat it as a pointer to the pointer. All right. So and that will enable me with dereferencing it twice, hopefully. So then I dereference it twice, so I just didn't think that it could be like a good idea generally. Okay, so that could be a thing. Alright. Argument arithmetic, not a number or... Okay. What? Okay. So what if I try to do something like this, right? Where so is that a thing I can have? Okay, this is a thing I can have. So that's another pointer, and rereference it gives me 3. Aha. So that means originally here I just have to have 1. There we go. This is how you get the size of the stack. Yes. Because stack pointer so the stack itself is a pointer, right? But you don't know the type of it because you program an assembly, right? I tell it, okay, this is the type because it's 64 bits. All right, stack top is a pointer to the 64-bit value that is a pointer to the top of the stack. So there's 2 layers of indirection here. So here's the first layer, here's the second one. So we need to dereference once and use it as the top and subtract them together. This is the formula I was looking for. Try using char star, Zorzin, it's that simple. Imagine not trying to understand what I'm doing. Alright, so I wonder if I can... Char star is literally opposite of what I'm trying to do. Like, literally. Holy shit. Okay. So, this is basic script to set up the environment. Any asset in GDB script. That's a very helpful message. Okay, now a GDB. So yeah, on top of that, I want to do something like this: 1 back, 2 back. Tool, is it tools? I cannot reach it. 1, 2. All right, tools. x86, x86, 64 GDB. Nice, nice, and it doesn't fucking work. Epic. 5. What's up with 5? Oh, it's a okay. Long int. Cool. Cool. Now I can. That's really strange. Why don't you have TUI disable? TUI. I disabled TUI and this shit crashed. Okay. One more time. Oh, there we go. This is what I wanted. Oh my god. Alright. There we go. So we're pushing on the stack. As you can see, we have a value on the stack, and here's the size of the stack. Second value on the stack, second value on the stack, third value on the stack. So here is the stack, and this is the third value. And we're starting dropping the values. Right. So we dropped 1 value, here it is. We dropped another value, here it is. And we dropped the third value, here it is. Isn't that amazing? But don't you know, why do you say Linux doesn't have a decent debugger? GDB is so... yes. Look how cool GDB is. Look how cool it is. Oh my god. Alright, anyway. So we implemented drop, which is quite cool. Add. An ironically, Visual Studio Debugger is one of the better ones I've used. Yep, I do fucking agree with you. Seriously, same. Fucking the same. It's like a golden standard for C++ debuggers, which no one has ever been able to replicate. LLDB is also very slow, by the way, compared to GDB. Especially if you try to inspect like big structures, it can basically stall entire LLDB like very quickly. Add x86 64 GDB debugging script. Add x86 64 compiled examples. Add GDB script for 64 compiled examples. There we go. So this is what we're gonna have here. So also let's have a separate commit for that. Remove print i64 x86 64. Let's put it this way: system AMD64 implementation, because it was literally that. All right. Implement write drop instruction for 64 translator, and all right, another one, include debug info into x86 64 compiled examples. All right, we're gonna push that right into the repo. Oh shit. Okay, so what's gonna be the next instruction we need to implement? So BASM to NASM. Okay, to do. So yeah, we should officially declare that drop is implemented. Next one, divide I. To be fair, like division, oh my god, division is not going to be the same as minus, because division in x86 64 is kind of annoying, right? It has to be like it racks and whatnot, right? Sorry. Yeah. So when you're doing, yeah, Intel, thank you so much, Intel, very cool. First of all, let's actually do the stack thingy. Right, let's do the stack thingy. So I extracted stack, then I'm going to be moving the top of the stack to racks. So now I have the whatever I need to, well, not really actually. So it has to be, I think, RBX. Right, so here's the RBX. So this is the top is the second argument actually. Then I subtract this entire thing. I can do it by 1, and I save another one to racks. So now I have a racks and RBX. On top of that, I think I need to not forget to XOR DX, literally, because the remainder, if I remember correctly, will be in the DX, right? It will be in the DX. You know what's funny? Like div I and mod I literally is the same implementation, it's just you take the result from different places. Alright, so then after that I'm gonna do well, div I, so that means I have to do idiff, if I remember correctly, right? So I have to do idiff and I divide by RBX. So racks will contain the result of the division, right? Racks will contain the result of the division, and DX contains the remainder. So, but we can throw it away, right? Okay, so after that is gonna be move RSI, and what we're moving there, we're moving racks. So moving racks to RSI. Then I need to increment, add RSI BM word size, and save it back to the top of the stack. Save it back to the top of the stack. So I move stack top RSI. I guess that's it. That's how you implement divide, I think. Cool. Is it gonna work? Is it gonna work? It seems to be compiling. So ASM, where is the ASM example? So div I. So here's div I, and it was implemented successfully. Now I'm gonna go to you know, my 1, 2, 3 BASM example, and in here I'm gonna just do push for 20, then push 2, and I'm gonna do div I, and I'm gonna just divide it by 2. So, and then we're gonna hold. So There we go. Alrighty, so let me see. Okay, so we're pushing 420 on the stack. There we go, we have 420 on the stack, then we push 2 on the stack, and we're about to perform the division. MDB. Cannot find it, sorry. Oh, it's an Open Solaris modular debugger. What the fuck is this? Oracle, though. Okay, so we bring it back to the stack. So we perform all of this thing. I think it worked. It divided 420 by 2, and the size of the stack is 1. So I think it worked correctly, right? Division worked correctly. Okay, so let's go. So division worked correctly. I'm not gonna do that yet. Alright. Implement div I instruction for x86-64 translator. Rakel means coffin in Romanian. Rakel? Or Rakel? I don't know how to speak Romanian, I'm sorry. It compiles, ship it. Yeah. Okay, so what's the next thing? We need to do modulars shite. Right, we need to do modular shite. It ships compiled. Okay. Haha, very funny. Very funny. So I'm gonna do a God code remove chat. We need to implement mod I, right? We need to implement mod I. Guess how I'm gonna implement mod I? Okay, so and we're using Rax, but I'm gonna literally do RDX. So that's it. That's the implementation. God code remove. So let's actually see. I want to try a couple of things here. So it's gonna be like 5. Modular 10, and it's going to be mod I, so it should give you 5, right? And another one is going to be push 2, I think. Then you push 10 and mod I as well. So let's see how it's going to go. Cool. So pushing 5, we're pushing 10, and then we're doing mod I. Saving it back, and okay, so at the end we ended up with 5, and the size of the stack is 1, so that's exactly what we expected. Okay, let's push more shit here. So there's 2, and then we have 10. Well, that was dumb. Excuse me. This is not what I wanted. I wanted to have 12. So that's what I wanted. I wanted to have 12. Very sorry. One more time. So okay. So here's a mod I. Here's a mod I. Okay, in mod I we ended up with 5. Then I push 12. Then I push 10. Right. Then we're doing mod I, and it should end up with just 2. There we go, I ended up with just 2, and the size of the stack should be 2. So we have 5 and 2, so mod I worked correctly. We successfully implemented it. Cool. Isn't that amazing? Isn't that amazing? I think it's good and amazing, mate. That's pretty cool. Okay. Implement mod I instruction for x86-64 translator. Let's push that right into the repo. So where's another thing? So another to do. We need to implement jump. We already have conditional jump. Unconditional jump should be a little bit easier to implement, right? Should be a little bit easier to implement. So jump generally takes the value from the stack. It consumes that value from the stack and just jumps there. Right? It just jumps there. So another the way how we do that actually, we take insta map. Oh wait, conditional jump. Does jump takes the operand actually. Jump takes the operand. Okay. Wait a second. Let me take a look at the natives. GNP. Yeah, jump doesn't even touch the stack. It just jumps to the operand. So that means, here's the thing. This is how we do that, literally. So, yep. You just jump there. Right. You take the instruction map first of all. Then you use the operand to translate. You translate operand to the instruction, right? And you just then jump there. Yeah. So that's how you do that. Where's PogOmega? I don't know. I think FFZ removed it. I think FFZ removed everything related to the PogChamp guy. So I didn't remove it. Yeah, I guess FFZ is also like Twitch. It is what it is, sorry. Okay, let me try to test all of that shit. So I'm gonna go to 123i, and what we're gonna be doing here is I'm gonna just push. First we can just push one, right? Then we're gonna have a label forever. Right. And I duplicate 0, push 1 plus I, right, and then I do jump forever. There we go, you see? So, and it will just, generate, fill up the stack until the stack overflows or something. Basically like this. Forever and ever. That's a nice one. Alright. Okay, let's see. I'm a robot.
17 месяцев от часика ей.
Thank you. Thank you so much for 17 months of tier 1 subscription. Thank you. And welcome to our epic x86-69 club. Thank you so much. Fucked up the ending a little bit, but yeah, overall it's Russian. So yeah, the ending should be Yev, not U. Yes. But who cares about grammar, right? All right. So let's fill up the stack with numbers. So we do a dup. So we duplicate it, then we increment it by 1, and then we're gonna keep filling it with something until the time has come to fill it up. Okay, so then we jump back there, and as you can see, our stack being filled with 1, 2, 3, 1, 2, 3, 4, and so on and so forth. Yeah, this is how it works. Yeah, as you can see, the unconditional jump works. It fills up the stack. So yeah. So that means I'll have to go here and just remove this to do. And down there. 105. Implement jump instruction for x86-64 translator. Very funny. You guys are so funny. Alright, so what's the next to do? We need to do return and call and also write. Oh, and also read 8 and write 8. Holy shit. Okay, so that one is interesting. By the way, ret is similar to jump, except we take the address not from the operand, but from the stack. That's literally what it is. That is literally what it is. Ironic saw the thing in the wild recently. It was pretty... Dude! I see it in the wild every fucking day. So... well, almost. Alright, so... yeah. Anyway. So we still have these instructions to implement. We still have these instructions. My parents send me this shit every time they text me, so... anyway. Yes, exactly. And I use it every day. Russian life. I'm a little bit tired already. I'm going for the 6th hour, I suppose. Yeah. That's the rest of the instructions we need to implement. I don't want to call them to do because they are not going to be particularly issues. So I'm going to go ahead and replace them with fix me. Right. So that's what they're going to be. Alright. I'm going to move this thing here. Fix me, senpai. Yes. 105. To do. Fix me. Alright, let's push that. So this particular issue already becomes quite heavy. Yep. So did I create a pull request for it? Okay, let's create a pull request for it. So it's already too big, so I have to be a little bit careful with how I do all that. Okay, so it's gonna be something like introduce dump u64 function and deprecate print u64 native function. And it's not gonna really close 105, but it's gonna contribute to its completion. Alright, so let's wait. Is it ready? Okay, so we're gonna wait for continuous integration. So that's a lot of changes, I think. So we have that. Better way of allocating. Okay, so we have some to-dos. Let's actually snitch them up. Report, prepend body, introduced in 126. Wait. Detected project BM. And wait a second. Will you? Okay. Did I fuck it? I probably fucked it up. Module introduced in. Yeah, I probably fucked it up. Okay, so that's okay. Alright, so that's a pretty epic shite. But we still haven't managed to make this entire thing compilable fully. Making a coding language. I'm actually making a virtual machine with its own assembly. Right. You can check it out here. So I'm making my virtual machine with its own assembly, and on top of that I make the assembly compilable to x86-64 assembly. So yeah, you can find the source code of this thing here, and somebody submitted something. Let's take a look. Hopefully make readme easier to read. Okay, I'm gonna take a look at that later after the stream because it's in a different project, so it's off topic. Alrighty, so that was a lot of changes, but yeah, I can finally merge that. That's pretty cool. So yeah, today was a very productive stream. We shaved a lot of yucks. To be fair, like shaving those yucks was worth it because now we have more features, right? Because now we have character literals to some extent, right? So they're pretty big, but we have them. So we can now inspect memory in BDB on some rudimentary level, right? It's not perfect, but you can do that now. Also, we implemented some other stuff. We introduced the notion of an entry point into the file format. All of that was really needed to move the project forward. And I feel like I'm bullshitting in like with the manager bullshit. Yeah. Anyway, but I think today's stream was pretty productive. So we started to migrate from native calls to the standard library. So our standard library is going to be a little bit more heavy. So majority of these things are going to be implemented in Bosom, which is really cool because that means the more we implement in Bosom, the more the standard library is going to be portable, right? Because then if we implement translator for ARM, all of these functions are going to work on ARM without us actually doing something with them. I think that's actually pretty cool, right? So yeah, so now print U64 doesn't need to be re-implemented in ARM, right? It's just, yeah. Bosom will become sort of like intermediate representation from an LLVM, right? We're literally implementing an LLVM at this point, so, but yeah. Also, to be fair, BM is something like between LLVM and WebAssembly, right? So, yeah. So you can use it both for the purposes of LLVM and WebAssembly as well. And we even created some issues to create translators that will translate Bosom to WebAssembly. So yeah, we will have Bosom to Wasm, for example. So that'll be interesting. LLVM. Yeah. Bosom web app. Yeah, so if we implement this translator, it will be technically possible to implement a web application in Bosom. So, yeah. To be fair, virtual machine is really close to WebAssembly, so... but anyway, it is time for me to go, boys and girls. I'm streaming for 5.5 of an hour, and today's stream was actually such a shit show with all this internet and Twitch problems. It is time for me to go. It is time for me to go. Thanks everyone who's watching me right now. Really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow we're gonna continue doing all of that stuff and hopefully make this thing finally translate to x86-64. So tomorrow we're gonna continue doing these things. Check out our schedule for more information on different projects we're working on. Check out our VODs channel where we archive all of our streams. This stream is gonna be there but tomorrow. And also check out our Discord server for offline discussion with the community. And I see you all tomorrow. I'm gonna go eat something. I'm really fucking hungry. Love you all. Mwah.